bachelor students from Moscow Civil Engineering University and also some geotechnicals from Moscow region and Russia participated and also participate now. And also now is coming also some professors also now we have some coffee break. But anyway, you know, it's time's extremely going well. So we must be, I think it's beginning better. So we have here Vice President of International Geotechnical Society, Professor Shin. He yesterday received medal of Gersivanov from Russian Geotechnical Society, officially in plenary session. So I have some moderator here, Professor Чунюк. He was come now with me. Ага, да, окей. По статусу. Да? Ага. Давай, водички туда. So, Professor Чунюк Dmitry, he is Dmitry Yuryevich. He is the head of Department of Geotechnical Engineering and Soil Mechanics of Moscow State Civil Engineering University. And another moderator I have here, Dr. Шулятьев Олег from НИУ. It is a famous research institute in Moscow, which related with foundation engineering and engineering geological investigations in the all Russia. He will become also soon. So we have several speakers from foreign and from Russia. So I want to inform you about customer for each presentations. So each presentations will be 15 minutes, 15 minutes. So we want to give some questions, if possible, maybe one questions, because not so many questions, because we have a big amount of presenters, unfortunately, maybe better say fortunately. So this is another moderator now come, Dr. Шулятьев from НИУ already I told you. So first presenter will be Professor Magdi Karkush, so University of Baghdad. He is president of Iraq Scientific Society for Soil Mechanics and Foundation Engineering. He also organized already two conferences. Each year organizes conferences in Iraq, especially 2 years ago in Baghdad and 1 year ago. And this year he organized a conference in Erbil, in North Kurdistan. North Iraq is Kurdistan region. So very good conferences. And also he made revolution in Iraq, in Arab country, because the number of Iraq society is very increased. So now we have elect Vice President Professor Albert Show. So he, I think, will be happy to have such active president from Iraq. So maybe Professor Magdi Karkush helped to us open Saudi Arab Society and Emirate Arab Society. We hope, and Kuwait, also Qatar. So it is need some revolution, fresh wind from Babylon. So Magdi Karkush also work in the University of Babylon also. So his topic for presentation investigations, the impacts of nanomaterials and the mechanical properties of gypsous soil. So please, Professor Karkush.
Thank you, Professor Askar. I am very happy to be with you in this conference. Also, I would like to thank all participants in this conference, especially from foreign countries. It is nice to meet you all friends. Mostly we are meet in symposiums or workshops before, but now I will present my paper in this conference. If it is a presentation, it is appear, please let me know. It's okay or not?
We show your presentations.
My voice, it is okay or not?
Your voice is very good voice.
Thank you very much. Thank you very much. My presentation is Investigation the impacts of nanomaterials on the micromechanical properties of gypsum soil. This paper or this work is a part of PhD thesis submitted to the University of Baghdad 1 year ago. This paper presented by Mehdi Karkoush, speaker, Alal Murshidi, and Professor Hussein Karim. Outline of presentation: introduction, objective of study, soil sampling and nanomaterials, preparation of soil samples, testing program, results and discussion, conclusion, references. Introduction. Gypsum soil mostly consists of CaSO4 to H2O, which separated in wide areas in Iraq and cover about 31% from Iraq. This soil can be classified as strong when it is dry, but mostly lose its strength upon wetting or soaking in water. We have a serious problem in Iraq, especially in Mosul Dam. It is considered the most dangerous dam in the world because this dam storage large quantity of water, about 11 billion cubic meter, but this dam is founded on gypsum soil, so it is considered a very big serious problem to us because you are constructed a hydraulic structure on a gypsum soil. So this map showing the distribution of gypsum soil in Iraq. Mostly this soil distributed in the west and south of Iraq, as shown in the map. Objective of study. The present study object aims to improve the geotechnical properties by using nanomaterials. In this study, two types of nanomaterials, nanoclay and nanosilica, was used, and each one was mixed in 3%, 1, 2, and 4% to see the effect of such materials on geotechnical properties, collapsibility of properties, mechanical structure, micromechanical structure of soil after mixing with nanomaterials. Soil sampling. Two soil samples of gypsum soil obtained from a depth of 0.5 to 1.5 meter below natural ground level. And the first soil sample obtained from a Najaf governorate, which contains about 42% of gypsum, and the second soil sample obtained from a Sumawa governorate, which contains about 54% gypsum. The soil samples obtained from two cities tested in the laboratory of soil mechanics and foundation engineering in Baghdad University, and some of the physical properties are shown in table 1. So the first soil sample from a Najaf city can be classified as SM, but the soil sample obtained from a Sumawa city can be classified as SPSM, with low relative density, with low dry density, as seen in table 1. The chemical properties of gypsum soil shows mostly the gypsum content, which is about 42 and 54% in the two soil samples, and other properties may be useful for chemical reactions between nanomaterials and the chemical composition of soil. The particle size distribution of two soil samples is shown in figure 2. Mostly the soil sample obtained from Al-Sumawa city can be considered poorly graded soil sample, as shown in the figure 2. There's narrow range of particle sizes in this soil reflect the poor graded of this soil. But the soil sample obtained from Najaf city also can be classified as well graded, but there is a gap in some sizes of particles. Nanomaterials. Two types of nanomaterials are used in this study. Nanoclay materials, which is a new generation of manufactured clay with a wide range of nano composites of high performance cement. Also, nanoclay has a phyllosilicate or layer structure with thickness of about 1 nanometer and about 150 to 300 nanometer on one-dimensional surface. Nanosilica, cab or cell is the name of nanosilica used in this study. The chemical and physical properties of nanosilica used in this study was tested according to the specification of American Society for Testing and Materials, C 102403. The physical and chemical composition of nanomaterial used in this study are shown in table 3. Mostly the color, the physical form, the density, the particle size. The particle size of nanosilica about 11 to 12 nanometer, and the nanoclay is more finer than nanosilica, so the size about 1 to 2 nanometer, and the specific surface area of nanosilica about 200 centimeters square per gram, but for nanoclay 220 to 270 centimeters square per gram. Specific gravity of two materials is shown in table, also humidity and chemical composition. Preparation of soil samples. The two soil samples, after drying and grinding, were mixed with each were mixed with a 3% of nanoclay and the 3 ratios of nanosilica, 1, 2, and 4. Then this soil sample left for curing for 24 hours. Then we are starting the testing program. Figure 3 shows the preparation of soil sample and mixing the gypsum soil with nano clay and the curing for 24 hours. After that, we can test. Also, we are curing for 7 days to check the effect of nanomaterials on the shear strength parameters of soil. Testing program. The testing program on two soil samples. Each soil sample was mixed with 1, 2, and 4% of nanosilica and nanoclay. The effect of curing time also investigated: 24 hours, 3 days, 7 days, and so on. The effect of soaking on the shear strength also was investigated to see. Mostly, as I said before, the gypsum soil is strong when it is dry, but losing its strength upon wetting or soaking. So it is so important to investigate the strength of gypsum soil upon drying or wetting. Table 4 shows the test conducted on the two soil samples, mostly starting from physical properties, specific gravity, particle size distribution, compaction, hydraulic conductivity, and collapsibility test, direct shear test, unconsolidated end-grain triaxial test, pH, gypsum content, X-ray diffraction, FESEM, FTIR, and loss settlement. These three tests were used to study the effect of nanomaterials on the mineralogical composition of gypsum soil after treatment. Results and discussion: gypsum content and pH value. Mostly the gypsum soil, the gypsum content of soil reduced after mixing the soil sample with nanoclay and nanosilica. Before mixing was 42% for a Najaf soil, but after mixing with 1% of nanoclay, the ratio of gypsum content reduced to 39, and 2% of nanoclay reduced the gypsum content to 37.5, and 4% reduced the gypsum content to 35. It is very important to focus on reducing the gypsum content in the soil to reduce the negative effect of such a component on the geotechnical behavior of soil. Also, the nanosilica used in this study reduced the gypsum content, but with a little ratio than using nano clay. Specific gravity and hydraulic conductivity. The specific gravity of soil samples mixed with the nano clay and nanosilica increased, because already the specific gravity of nanomaterials is higher than the specific gravity of gypsum soil, which is mostly lower than 2.5. So using nanoclay or nanosilica will increase. Also, increasing the percentage of nanomaterials, nanoclay and nanosilica reduce the hydraulic conductivity of gypsum soil sample. That is happened because cementation between soil particle resulting from adding the nanomaterials, also closing the continuous path inside the soil samples. Compaction test, we can see that using nanomaterials, first, increasing using nanomaterial will increase the dry density of soil. But on the negative side, increasing the percentage of nanomaterial will increase the percentage of optimum moisture content required to achieve the maximum dry density. This resulting from increasing the surface area required for wetting, so increasing the quantity of water added to the soil sample to achieve maximum dry density. Also, we can look for shear strength parameters, cohesion, and angle of internal friction was investigated. The shear strength investigated by using by testing direct shear test and UU test. It can be seen that cohesion is much higher in the dry state than in the soaked state. Also, there is a slight increase in the angle of internal friction after soaking. This behavior may be attributed to the destruction of the bonds among the soil particles, which resulting from dissolution of cementation salts after soaking in water. The soaking has a significant influence on the apparent cohesion, but the angle of internal friction is slightly affected with soaking. The results of cohesion test or cohesion and angle of internal friction are shown in figure 5. Also, we can see increasing both the angle of internal friction and the cohesion with increasing the percentage of nanosilica or nanoclay for an edge of soil. The same curves were obtained for Sumawa soil samples, but the effect of nanomaterial on the angle of internal friction is very few, as we can see in the two lines in red and the black. But the effect on green and the blue lines, it is very significant, can be considered significant, which is represented the cohesion before and after soaking. Compressibility of soil, one of important property is the collapse potential of gypsous soil. So it was 15.6 for a Najaf soil and 17.15 for a Najaf soil. The collapse potential was tested by using single oedometer test and tested at a specific stress, which is about 100 kilopascal. So we can see that mixing the soil sample with nanomaterial will reduce the collapse potential significantly, but there is no significant difference between the three ratios. We can use 1%, it is enough to reduce the collapse potential and have almost the same effect like 2% and 4% of nanomaterial. If we know that the cost of nanomaterial is still expensive, and if we reduce the percentage of mixing, also we reduce the cost of soil improvement. The same behavior.
Professor, you have 3 minutes.
Okay, I will finish my presentation. Also, we conducted several tests to measure the effects of nanomaterials on the chemical components and the microstructure of soil, gypsous soil sample, such as X-ray diffraction test. From this test, we can see there is erections depend between the nanomaterials and the gypsous soil, which depends on the chemical and mineralogical composition of each soil and additive. Also, quartiles X-ray diffraction test peaks are slightly higher than that the mineral peaks, because quartiles is better separate X-ray than other substances which is available in nanosilica. The peak was identified as a quartiles at 24.36. Also, X-ray diffraction test patterns, and it is obtaining peak angles value and intensity for untreated and treated and Najaf gypsous soil is presented in figures below. Also, we can make a series of Fourier transformation infrared analysis. In this test, we can measure the spectra of soil particles, and depending on the spectra, we can classify the chemical and composition or compounds of soil sample. The results of such tests are presented in figure 10 for a Najaf gypsous soil. Also, we can see the field imaging scanning electronic microscopes, ISSMGE EM, that shows the change in the macro and microstructural development of gypsous soil due to the addition of nanomaterial. And we can see that the curing period is very important to give a time for reactions between the nanomaterial and chemical compounds or minerals present in the soil. So we can see that the image in A shows the gypsous soil before mixing with the nanomaterial. After that, with mixing with 1% of nanoclay, and B, so some of voids closed by nanomaterials. Also in C with 2% and D with 4%. Mostly the voids between soil particles are closed by cementation resulting from mixing the nanomaterials with soil particles. Same behavior was noticed for the soil sample mixed with nanosilica, but mostly the nanoclay is more better than using nanosilica. Conclusions: mixing of nanomaterials with gypsous soil causes significant reduction in the compressibility of gypsous soil, but no worth from mixing more than 2 or 1% of nanomaterial. There was a significant increase in the apparent cohesion of soil resulting from the cementation of soil particles by nanomaterials, but a slight increase was noticed in the value of the angle of internal friction. Also, the collapse potential of soil reduced after mixing with nanomaterial, but no worth for using more than 1% of nanomaterial for both nanosilica and nanoclay. The hydraulic conductivity of compacted soil sample or treated soil sample was reduced after mixing with nanomaterial, and the percentage of reduction in coefficient of permeability or hydraulic conductivity increased with increasing the percentage of nanomaterial mixed with the gypsous soil. The treatment of gypsous soil by nanomaterial increased the maximum dry unit weight, but at the same time increased the quantity of water required for permeation of the soil sample. The result from X-ray diffraction, FTIR, and FE-SEM analysis indicated a new phase of the chemical activity of soil compounds treated by nanomaterials. The effectiveness of the treatment depends on the type and the quantity of additives, type of soil, curing time, and pH of soil, which play an important role because nanomaterial mostly acidic and may reduce the acidity of the soil samples. References used in this paper. Also, I would like to invite you to the 3rd International Conference on Geotechnical Engineering Iraq on 17 to 19 of May 2022, which will be launched in Baghdad University. This conference organized by the Iraqi Society for Soil Mechanics and Foundation Engineering in cooperation with College of Engineering at University of Baghdad and College of Engineering at University of Karbala. Thank you. Spasiba. Sorry for exceeding time.
Thank you very much, Professor Karkush, for your excellent presentation. It is also very thank you for inviting us for Baghdad next year conference. So please, one questions from auditorium. So Professor Shin, Yeonchul, please.
My name is Yishi Shin from Incheon National University in South Korea. Thank you very much for your excellent presentation. And I really happy to see your innovative nanomaterial. And I have a question about where can you use this innovative material? And our second question is, if you want to apply in the field, how can you, maybe methodology of the field application? Thank you.
Thank you very much, Professor Shin, and nice to see you in this conference. Actually, the nanomaterial still have little applications and started in the labs in general, but the application will be transformed to the field. Type of soil is important, and as we said, the gypsum soil in Iraq covered about 30% from the area of Iraq, so it is important to use such soil. Need to improve the geotechnical properties of some soil, especially this type of soil is very strong when it is dry, but when subjected to wetting or soaking, surface runoff, raining, will be very weak, and compressibility is very high. One of the big problems, as I said, we have a big dam constructed in 1980s in north of Iraq at the Mosul city, constructed on gypsum soil. So, and storage a very huge quantity of water and very high level of water storage in this dam. So it is, they are using injection by cement material to control the leaching of gypsum from the soil. At this moment, we can thinking by using a small amount of materials, but more effective, such as nanomaterials. One of the technology can be used, or technique can be used, is injection after mixing with water, as in cement, which will be now injected in Al Mosul Dam. Also, there are many techniques now for deep mixing of soil. We can also apply, instead of using cement, we can use small quantity of nanomaterial, but will give very promising results for improving the geotechnical properties of soil. But these hopes may be not used now, but maybe in the future will be used widely, especially when we search about nanomaterials. Every day we can find a new generation of nanomaterials. So every type of nanomaterials have different influence on the geotechnical properties of soil, if we are talking about geotechnic, because we are a geotechnic. So we need to know the properties of nanomaterials and properties of soil, and what can happen from chemical reactions between nanomaterial and gypsum soil. But almost still we can use deep mixing for mixing the soil with nanomaterial, or we can inject the nanomaterial after mixing with water, as in cement injection.
So thank you, Dr. Karkush, for your introductions. So now is no time for discussions, for questions. So thank you. So next presenter will be Professor Dervin Chan. Professor Dervin Chan from Tamkang University, New Taipei City, Taiwan. So his presentations related to its performance of barrette under horizontal load. So Professor Dervin Chan, also one of key person of Chinese Taipei Geotechnical Society. He organized 2019 16 Asian Regional Conference, very successful. More than 1,000 people come from different countries, including Kazakhstan and Russia. And also Professor Dervin Chan also invited professor of Eurasian National University, and also he is one of biggest specialists of piling and deep foundations. So please, Professor Dervin.
Okay, Professor Askar, thank you very much for inviting me to these seminars. I want to say hello to our Russian colleagues and all the colleagues online. Okay, I'm trying to share my screen to you. Did you see my screen?
Yet.
Okay, all right.
Now
Okay.
it's coming, but we wait.
Is this okay now?
Okay.
Okay, this is the title of my presentation is Performance of Barrette under the ladder load. And this is selected from a recent paper we published. And Professor Askar is my co-author. Okay. And this is the introduction of my presentation. And for this study, the deformational behaviors of the barite under the lateral load in clays and sands were studied by three-dimensional finite element analysis. And the longitudinal and transverse direction of the load were considered. This is very important. And when we see the barite, this is the longitudinal direction, okay? The cursor that I point out in the longitudinal direction means the load applied in the lengthy direction. And when the load applied in the short direction and the short direction of the barite, it means the transverse direction. And the definition of the long and the ridge barite was try to suggest it in our papers. And this is the paper I mentioned. It's the original name of this paper is the length inference on ladder performance of barite from three-dimensional finite element analysis. It's published in Journal of Applied Science and Engineering. It's a journal hosted by Tankang University. Okay, the tool we use in this study is the program called Midas. Midas GTS NX is the program we use. A single barite is studied. The size of the single barite is 2.8 meter times 1.2 meters. I mean the length and the width was embedded in the clay or the sandy soil. It was assuming this is a homogeneous soil profile with its head above the ground surface. Finite element mesh was discretized with a node or the 6 node. It's just like cake or cake shape and the cubic shape solid element. Essential boundary condition such as the rollers and the hinges were modeled. Horizontal load was applied at the height of 1 meter from the ground surface. And this is the schematic plot of the structure system we studied. And we try to make some validation of the analysis. As you can tell, we try to increase the size of the mesh to enable to obtain the stable and the converged solution from the analysis. And also, we made some comparison between the studies shown by other people using such as the program Abacus, also a finite element program. And this is the structural geometry and the material parameter of the numerical model we studied in our paper. And the structural geometry shows that the barite has, this is the length, 2.8 meters I already mentioned, and the width and the length of the barite has two type of lengths. One is a long barite, the other one is a short barite. Respectively 50 meter and 20 meter. Zone of the soil is, we tried to change the dimension to see if we would be able to get the stable solution. So finally, we stopped at 50 meter, 50 meter, and 80 meter, okay? The length of the finite element zone, the width of the finite element zone, and the thickness of the finite element zone. And the material parameter shows here. This is the concrete and the clay soil and the sandy soil, because we consider the type 3 soil profiles in Taiwan. And the shear wave velocity of the type 3 soil has been restricted within 180 meter per second. So we try to choose 120, 150, and 180. For clay and the sandy soil, the Poisson ratio is different, a little bit different. And the unit weight is a little bit different. We assume for the clay, it is an on-drain condition. So the correlation between the Young's modulus and the on-drain shear strength has been used. And this is the calculated on-drain shear strength, 3252 and 76 kilopascal. And for the sandy soil, the shear wave velocity is the same. And also we use some correlation to calculate for the phi. C cohesion is 0. Okay, this is For sandy soil, we assume everything is drain condition. This is the empirical formulas we adopt. And we also try to consider the contact element. So for the adhesion and the friction angle between the, between the soil and the concrete, we use these two equations to calculate for the parameter of used to be in the for the parameter to be used in the for the concrete element. And this is the nominal length of the pi in clay, which has been suggested by Davidson and Gill in 1963. They call this parameter as R. R is related to the Young's module of the concrete, moment of inertia of the concrete divided by the K. K is this, some terminology called the relative stiffness between this pi and the soil. It has been suggested as this equation. Anyway, to calculate this type of things, you need to use the equivalent diameter of the barrette. In their study, for a single pi with length L, it was suggested that the L divided by R greater than 5, the pi is called a long pi. If L over R less than 2, then the pi is called a ridge pi. Similarly, in the study by Mellock and Rees in 1960, they call the nominal length of the pi in sense as a T, and the T is related to the NH. NH is the coefficient of subgrade reaction. The coefficient of subgrade reaction can be approximated by knowing the shear wave velocity of the soil, which has been suggested by Caselli in 2012. Okay, and we calculate it as 4,600, 6,000, and 8,000 kilonewton per cubic meter. And similarly, L divided by T greater than 5 is for long pi, and the L divided by T less than 2 is for ridge pi. We use this kind of concept to finally determine what would be the long condition, definition for the barrette, and the shorter or the rigid condition for the barrette. And this is the Rx, Ry, and the Tx, Ty in our study we calculate, because our shear wave velocity has been, changed from 120 to 180, and in clay and in sand you can calculate different R and the T. Okay, and the Rx and Tx means that the load was the load was in the transverse direction of the barrette. And when the load was in the longitudinal direction of the barrette, then we calculate Ry and Ty. Okay, this is some plots trying to show the lateral load behavior of the barrette in clay. This is the load was in the transverse direction. And as you can tell, this is the load displacement curve recorded at the pi head. And this is the deflection of the barrette. And this is the bending moment along the barrette, and the shear along the barrette. Because everything was done by finite element analysis, for the bending moment and the shear force, we need to calculate, from the deflection of the barrette. Because from the moment, this is the second derivative of the displacement. For the shear, this is a third derivative with respect to the displacement. And as you can tell, this is a short barrette, this is long barrette. The largest displacement won't be changed very much, by the length of the barrette. Okay, because the displacement, the largest displacement are about the same order. And this is the thing for the load in the longitudinal direction. And this is a short barrette, and this is long barrette. As you can tell, if the load was applied in the longitudinal direction, and the largest displacement will be reduced. Okay, if you compare these plots, you will find out if the load was in the longitudinal direction, if the same load was loaded in the longitudinal direction, then this deflection will be reduced, of course. And this is the part related to the sand, to the result of the sand. Similarly, longitudinal direction. Okay, then we move to another. We try to look at the nominal strength, nominal length of the things. As I suggest, as I review the suggestion by Mellock and Rees and other guys in Clay and for Sam, we try to calculate these things in our study. And this is for the result for the calculation for clays. As you can tell, we try to normalize the deflection of the part of the barrel with respect to the nominal length. And this is the normalized thing, deflection with respect to the depth. And this is for the differential wave velocity. So yeah, okay. For longitudinal direction load, we find out that if L divided by Ry greater than 7, we can define the long barrel, and the L divided by Ry less than 3 is for rich barrel. For transverse direction load, if the ratio greater than 5 can be used for as a criteria for long barrel. No criterion is suggested for rich barrel because most of the things we calculate is always greater than nearly around or greater than 5. So we don't have the data, for the L over R ratio less than 5. So it's difficult to determine the rich barrel for the transverse direction load. Okay, this is the same thing for the same. So I go through the things quickly. For both transverse and longitudinal direction loads, L divided by T greater than 6 is for the long barrel, and L divided by Tx less than 2 is for the rich barrel. And
Professor,
lastly,
you have 3 minutes.
Okay, I'm about to finish. Lastly, we try to compare, the chance formula. The chance formula is very famous. It was brought up by Professor Zhang Youling is a Chinese American. He brought this formula in 1937, I think, very early. We try to compare his analytical suggestion, analytical formula with our finite element solution. We find out, analytical formula suggested by Chang in 1937 on single pi subject to ladder load was found adequate for the barrel in the case where the load is applied in the transverse direction. In order to resolve that, equivalent pi diameter must be used and must be obtained from the moment of inertia of the barrel. In any case, if the load was applied in the longitudinal direction, the analytical formula would underestimate the bending moment along the barrel. This is all the things we found in this paper. If you are interested, you are free to check this paper. Thank you very much for your attention.
So thank you very much, Professor, for your interesting presentations. So we have time for one questions. Please. Yeah, very understandable, huh? Okay. So thank you very much, Professor Derwin.
Thank you.
So you made very good presentation. So no questions, very clear.
No questions.
Thank you.
Thank you very much.
Thank you.
Okay, please check everything from the, if you are interested, please feel free to check our paper. Thank you very much.
By email or in future, we will communicate with you. Thank you.
Thank you.
Thank you. Next presenter will be Professor Victor Kalyakin. So Professor Victor Kalyakin from University of Delaware, Newark, United States. So Professor Victor Kalyakin, he's originally from is Russian, but he is born in the United States. He's American. He has American nationality now, and also he is one of very famous professor in the United States regarding of numerical analysis in geotechnical engineering. So he published several books and several papers more related with soil structure interactions by using of numerical, his own program of Kalyakin program. And also he is graduated in the University of University of Berkeley University. He obtained a PhD here, and also he is now is one of representative of our university, also visiting professor of Eurasian National University. So today his presentation more related with load capacity of geosynthetic encased soil columns bearing and on a compressibly soil layer. So please, professor.
Большое спасибо вам за вступление. Good morning, good afternoon, depending on where you are, to all my colleagues who are attending. I'm going to try and share my screen now here for the presentation. Hopefully you can see this. Is that okay? Can you see?
Yes,
yes,
yes, professor, yes.
Yeah. My topic today is indeed load capacity of geosynthetic encased soil columns bearing on a compressible soil layer as opposed to a rigid one. My co-author is Ali Al-Sadi, a recently defended PhD student at our university. In fact, we'd like to acknowledge a few people before starting. First, my previous student, Majid Khabazian, who's some of the work I'll present here. And Ali would like to acknowledge the Higher Committee for Education and Development in Iraq. They sponsored his PhD studies, and so we'd like to acknowledge that support. My presentation, because of short time, has only 4 pieces. Following some general remarks, we'll talk about the simulation of single geosynthetic encased soil columns bearing on stiff strata. That's a traditional type of analysis. But the focus of Ali's work and our more recent work is on such columns not reaching stiff strata, and we'll discuss why that might happen and the ramifications. And then we finish the presentation by looking at single columns of this type not resting on a compressible layer, and some conclusions that are reached for such columns, and see how they compare to ones resting on rigid bearings. Now, let's start with the discussion of stone columns. Many of you are familiar with this technology. It's a ground improvement technology where a hole is bored, either wet or dry, in a soil, and then some kind of either gravel or sand or gravel and sand mixture is put in the hole, compacted, typically through vibration, and that creates a stone column. And many of these elements are relatively quickly created to give a foundation to sites, especially ones with possibly soft soils surrounding these columns. The soil columns are known to reduce settlements. It also increases stability. There's drainage benefits also, because typically the soil surrounding such entities is soft, and the soil columns themselves are quite permeable compared to the surrounding soils. The lengths of these that are attainable go between typically 3 and 15 meters, although nowadays they can be up to 30 meters installed with certain techniques. One of the problems, though, of a regular soil column is that when they are in very soft soils, typically with shear strengths less than 15 kilopascals, they will exhibit a lateral displacement called bulging, especially in the upper region. And this largely reduces the stone column's ability to take load and is a limiting factor in their application. These types of low shear strength soft soils, though, are prevalent in many parts of the world, and so people sought to somehow improve the stone column's performance when installed in such soft soils. The key was to encase these stone columns with some kind of geosynthetic material. Typically, these are non-woven socks, if you will. It's a tube with an end cap of the material. And because it is encased now, when there is load applied, the geosynthetic is mobilized, it provides confinement, and that, of course, increases things like bearing capacity, and it reduces the lateral displacement, which we call bulging. So this confining pressure then forms what we call the geosynthetic encased soil column, or the GESC, which will be our focus in the talk today. So needless to say that once this was realized, there was a good amount of work performed because the geosynthetic encased soil columns are used in geostructures where we can moderate relatively low to moderate construction-induced settlements. For example, the prime application was columns supported embankments, as shown here in the cartoon, where there would be some kind of either roadway or maybe a train running on such an embankment. It's sitting on these type of geosynthetically encased columns, then each one taking some tributary area of the structure above. And traditionally, these columns then would bear on a rigid base. And that would be the support from below, using end bearing, of course, as a primary support mechanism. Now, as I say, traditionally, these elements, either stone columns or the geosynthetically encased ones, have indeed been extended to a hard layer or stiff stratum, and therefore counting on bearing capacity. So the cartoon is shown here. You have some kind of applied load. This would be the column with the encasement and the bulge or the lateral displacement as shown. But the key here is that it's sitting on a firm stratum. And this provides, of course, substantial end bearing to allow load transfer. And extensive experimental results and numerical analyses were performed over the years to compare such geosynthetic encased columns to ones that are just unencased regular stone columns. And several years ago now, my former student, Majid Khabazian, and our colleagues, we did many kinds of analyses, from single column analyses to indeed modeling complete embankments, to looking also at the unit cell concept and so forth. I would like to just present a few of the results for a single geosynthetic encased soil column, but bearing on stiff strata. That's sort of to give us the reference of a traditional type of analysis. When you do such a simulation with careful modeling using a suitable program, you see that very quickly that when you compare the results of a stone column, shown here in blue, compared to a geosynthetic encased column, this is the lateral displacement for a vertical settlement of 50 centimeters. You can see that the benefits of using encasement are quite extensive, that the lateral displacement is clearly affected and is certainly much less than a regular stone column. The same thing goes for relative vertical displacement, again, a big effect, but even more so on skin friction, which I think many people understand better even than relative displacement. You can see that when we encase a column, the skin friction is affected substantially. This is, again, it's a single column, but certainly that would give an effect when you had groups of such columns in an actual foundation. Finally, load transfer mechanisms. If I look at a stone column by itself, no encasement, it has some end bearing here, and again, some skin friction. But compared to a geosynthetic encased column, you can see that much more end bearing, and again, skin friction is more sizable because of the addition of the encasement. So this led to the use of such encased columns in many applications. Again, typically sitting on a rigid bearing, a rigid layer or a stiff stratum. The realization came, though, that this is not always possible, that sometimes the deposits of clay are very deep or large, especially in coastal areas. And perhaps also we may not want to have the column extend completely to a stiff stratum because of economic reasons. So the question raised was, can we look at columns of these type, encased columns, but that are not driven to stiff strata, because this may be problematic. So the cartoon is here now. This is, you can see the similar kind of column encased again, but it's not resting on the firm stratum. There is some kind of what we call floating depth below the column for either economic reasons, or if in a very deep clay layer, maybe you cannot reach the stratum in a practical sense. So this is the focus of the work we're talking about today, looking at columns which are floating, if you will, not reaching that stiff stratum, to see how they behave. There is relatively few experimental and numerical studies of such columns, not surprisingly, because they are relatively new. Especially experimentally, there is some model tests, but they lack the full scale effects, which are interesting to us in the field. And especially numerically, there has not been a lot of work. So we undertook an extensive numerical study of such geosynthetic encased soil columns, but not resting on a rigid base, but having some kind of distance here between the end of the column and a firm stratum. We did several kinds of studies. Professor Derchen just talked about some numerical methods. This is a single GESC. Our analyses were done using Abacus. This is a quarter of the soil domain because of double symmetry. You can see that this is the encased material. Here is the floating depth. We used a surrounding soil that was either Bangkok clay or San Francisco Bay mud. The actual encased material was an actual soil such as Sacramento River sand or Santa Monica beach sand, for example. And so gained a lot of insight through the single column. This was extended then to actual geosynthetic reinforced soil column supported embankments. You can see the columns here are in blue. Below them is the floating depth. The rigid base would be somewhere down here. So this is modeling the actual construction of an embankment and the to a given height to see how these columns behaved, how the embankment behaved, and then looking at things like changing the spacing of the columns and other properties. We then also finally looked at the unit cell concept, which again relates to a full embankment, but it looks at just a one small piece of this. So the model looked like something like this, much simpler than the complete 3D model. This is a 3D unit cell model with, again, a floating depth below the base of the column, but above the rigid stratum. So extensively, this was analyzed, but now the difference being we now had floating columns in all these analyses. My focus here is on single columns because of lack of time. And I will present just some conclusions that we reached because, again, of lack of time, and can't get into any details. So we're modeling, again, a single column, as I showed a few slides ago, resting on a compressible layer. The first thing you need to check is how reasonable is such an analysis compared to a similar column resting on a rigid base. So here we have the solid line, a geosynthetic encased soil column resting on rigid base, an ordinary stone column, and this is the geosynthetic column, but resting on a floating base, a non-rigid stratum. So you can see that although it's not as good as the rigid base as to be expected, it's better than a ordinary soil column. So there is some promise to using such technology. Same thing with lateral displacement. This is the ordinary stone column, which we've seen before, very large bulging, but both the current case and the rigid base are somewhere down here. So again, much less lateral displacement when you encase a column, even if it's not resting on a rigid base. We found that in our analyses for both rigid and non-rigid based columns, the lateral displacements were about the same, and the bulging extended to about 7 or 8 column diameters when measured from the top of the column. So that meant that it did not matter so much if you were resting on the rigid base or floating, if you will, that the lateral displacement was still about the same and was greatly improved by the presence of the encasement. So that was an interesting finding, that it didn't matter what how the base was as far as the bulging was concerned. We looked then at the length of the column. Length is very important if you think about load transfer mechanisms, because you have obviously far less end bearing when you have a column that is not resting on the firm stratum. So you have to then discuss the effect of the skin friction, which of course is increasing with column length. In this case, we looked at 5 meter, 10 meter, and 15 meter columns, all of them floating in the sense that they're not resting on the firm stratum. And compared this again to a column resting on a rigid stratum. Now, initially, due to end bearing, short columns resting on a rigid stratum will certainly have high bearing capacity. So you see here, this is the rigid stratum GECS, it's here. This is a stress that can be taken by the columns, the bearing capacity. And for short columns, not surprisingly, because of all the end bearing, they're taking a lot of load. Whereas if the column is on a floating base, non-rigid base, the short column has substantially less bearing capacity, as shown here by the point as shown. However, when you increase the length of the columns now, you're increasing the skin friction in both cases, and the end bearing effect is being minimized as the column becomes longer. So you see this kind of convergence, which is kind of interesting. The one rigid on the rigid base, as you make it longer, and the one on a floating base, as you make the columns longer, where skin friction now is the big issue, they start to converge. And so as you get longer columns, the fact that it's not resting on a rigid base is not detrimental. So if you want to indeed not reach a rigid stratum, or can't because of financial constraints, as long as your column is suitably long, you may be getting the same effect as a column on a rigid stratum. That's an interesting finding, because it now makes these columns resting on non-rigid bases competitive to ones on rigid bases. A more interesting finding, perhaps even, was that the compressibility of the soft soil layer, the layer below the column, seems to be the key, and seems to largely determine the settlement at the top of the column. Okay, and why is that important? Because the column, therefore, essentially behaves as a rigid body, and therefore is essentially not displacing. So if you know the type of soil below these columns, you can sort of use them as rigid elements, very much like things like concrete columns or rigid columns, because they are not displacing themselves. They are settling as a rigid body roughly, and so therefore can be sort of analyzed eventually, perhaps, as a design element very similar to rigid columns, which the deformation is again negligible. This is an interesting finding because before it was not clear the mechanisms of load transfer and compressibility, but because the GESC behaves as almost a rigid body and is sort of governed by the deformation of the soil underlying it, this shows a lot of promise for this kind of technology. With this, I say спасибо за внимание, and I would address any questions if you have them.
Thank you, Victor Nikolaevich, Professor Victor Nicholas. So I think already you have some questions from chat. You can see your questions?
Yeah, in chat it says, in case of liquefaction during earthquakes, the risk of lateral spreading of stone column will produce a behavior similar to a column in soft clays. Do you recommend to use geosynthetic even in sandy soil in seismic areas? That's actually, this is coming from Mario Terceros. Thank you. This is an interesting question. We, in a different study, looked at such columns in sand, but they do show promise, but there seems to be a reluctance to use them because people say that when you have sand, you should use other ground improvement techniques. So I think to answer your question, it would be possible to investigate, but it's very unpopular. And so if you try and publish such results, they meet with resistance. So that's my best answer at this point.
Thank you, Professor Виктор Николаевич. Так, пожалуйста, вопросы из русской аудитории. Может, по-русски спросить, он по-русски знает хорошо, так что он изучал по воскресеньям русский язык. Когда американские дети играли в бейсбол, папа и мама его заставляли изучать церковь, так что он русский язык очень хорошо знает. Так, пожалуйста. So one question again from our Vice President.
Yeah, this is Ishishin. See, as far as I know, there is a empirical equation in the chart without the encasement for stone column, right?
Mm-hmm.
Basic and other people. And
Yes.
do you have any some empirical or any methodology to estimate the bearing capacity with the encased stone column, without conducting the plate load test or any loading test?
Yeah, that's a very good question. Empirical relations are and have been proposed. The trouble with that is that when you have a soft soil surrounding the such a encased column, you inevitably have to induce or take into account plasticity, and plasticity becomes very problematic in an empirical relationship because then it becomes a very difficult kind of solution, which lends itself probably better eventually to numerical analysis anyway. There are some, to answer your question, but they are relatively heavy in assumptions, and the assumptions have been questioned by many people. So they are there, but they're questionable. So I don't know if I would recommend them per se.
Thank you very much, Professor Victor, for your introductions. So time is extremely going well. So thank you very much. So we will move to another presentations. So good day for you, because I think in the United States early morning now, very early morning.
It's без четверти 7 утра.
Да. Доброе утро. Доброе утро.
Доброе утро. Большое спасибо.
До свидания. До свидания.
До свидания. Bye-bye.
Next presenter will be our Vice President, Professor Yeon Chul Shin. He is from Incheon National University, Emeritus Professor. He is also a Vice President for International Society of Soil Mechanics and Foundation Engineering for Asia. And also he is now is Emeritus Professor, but part-time work in university. And he's also working consulting company, Korea, consult related to his underground structures. So his presentations. Да. So his presentation will be safety assessment for underground structures and its countermeasure. And Professor Yeon Chul Shin, he's also long-time work like Vice President of Korean Geosynthetic Society also, so more related with geotechnical engineering. So now he will be participate. He will be participate in two conference. Is Russian forum of ABAM forum here, and after that he will be moved in Sunday to St. Petersburg. In St. Petersburg he will be participated in another international conference, geotechnical conference in St. Petersburg State Architecture and Civil Engineering University. So he, что получается, да? А? Сейчас он подойдет.
And its countermeasures. I think this is very interesting topic. And the first background of this problem and the mechanism of ground collapse and report on assessment of the underground safety impact. This is very important, and I wish Russia, the Geotechnical Society or Russian government adopt this methodology, because this is a real need, for the deep excavation in the city area, Moscow or St. Petersburg, and the field monitoring through various instrumentation for countermeasures. So there are several reasons to have a ground collapse. Natural reason, all the limestone area, Malaysia or southern part of United States, and many other countries where we have the karst area, limestone, they have a sinkhole normally, and the man-made, in the Russia, subsidence of a mining area, mining town, because of digging out, the coal, minerals, and so on. And also in downtown area, we have a lot of problem because of the tunneling, metro highways in downtown area, and without any controlling about, bracing system or the groundwater control, because the last one is water extraction from industrial area. That may be a big problem. and deep excavation for underground space development, basement in the for building and so on. So this is a panoramic view of the Seoul. We have Han River path through the downtown, and you see high-rise building there, right? So I'll talk about a little bit, because along the coast, the riverside, there's an alluvial area, okay? So that is no problem, the high water table. We have many bridges, crossing over the the Han River. I think Professor Akela Hasekawa talked about the maintenance of the bridge. That was very important also, We had one problem, maybe 15 years ago, bridge was collapsed, in the morning time. So many people died, and the bus dropped into the river. See, the population grows in Seoul, So we have about 50 million people, but half of the people, population lives in metropolitan area. Seoul alone, we have 10 million, but around the area, we have 50 million plus, So we have a problem to digest, all these, massive, traffics in the morning time and the rush hour. We got to need, some kind of methodology to digest those things, I know in Moscow, I found out a lot of, traffic jam or so on. So you spend a lot of money. Oh, panoramic, another view, underground. See, we have 17 metro lines and 380 kilometers on the way. So you can access any corner of the Seoul by the metro. So fantastic, And maybe the cost of the metro ticket, less than $1. $1 about, That's very cheap. Japan is very expensive, But Korea is very, very cheap. I don't know, Professor Yasake reaction, So it's a fantastic view, So we like all my students, their commute, to metro. And now, furthermore, we want to construct an express train underground, below ground 50 meter, high speed, Maybe from Incheon to Seoul, normally takes about 1 hour. But by taking the GTX, we say GTX, okay? Maybe 20 minutes you can reach, okay? So young people, they like to have that because the residential area in Seoul is very expensive, They want to live in a little bit outside of suburban area. Or the sinkhole, what occurred, The red dot is a sinkhole, see? Along the, this most of the sinkhole occurred in the southern part of the Han River because of the lot of development, So that's why this happening this phenomenon. And see the sinkholes and the ground excavation, we have a lot of problem, cracking ground surface or something. So and some people is sunk down here. So there are a lot of problem created. Not only Korea, we have 1,250 sinkholes. Oh man, disaster, So the people is very much argue about it. That's some of the example of the that sinkhole happened, natural and man-made, a lot of tunneling or so on. So this is another very high-rise building, 555, 500, Lotte shopping center right here in Moscow. I found the Lotte department, same company. They built it, 123, 123, and the 555. But fortunately, foundation, the bedrock is not very deep, maybe about 30 meters or something, Then we can find that the bedrock. So it's no problem, not like St. Petersburg. So fine, but here's a reservoir. What happened? They digging out this soil underground, and then the water in the lake disappearing, reducing. Oh shoot, So big problem, So here, so the government aware of this problem. Oh, what the hell? Oh, not taking this program. Anyway, we have another view. Oh. Okay, here we go. So we have a bottom one, last one. There was a metro, metro line under construction. Above one, there's a underpass. Okay, on the top there's a ground surface and the high-rise building there also. So meanwhile, we have a lot of sinkhole here, right-hand side, okay? Right-hand side, a lot of sinkholes there, left-hand side. So, and this shield machine, they're drilling the tunnel like this. And so we have sinkholes, several places, okay? So also we have old, tombs and so on the top. So, and we found out, after the tunneling, the shield tunneling, you should backfill, area. But all this backfill area comes into the underpass. So it's a problem, So like this, and not only in the Korea, but the other country, I know 2013, Professor Illichov, president of Russian, the Geotechnical Society, he came to Korea, my university. He presented a paper about metro construction work in the Moscow. You had, many years ago, you had similar problem, So like talk UK and the United States, you see that, very, I don't know how to express in the where, near to where, Florida. You see, all of a sudden, high-rise building, apartment complex collapse, Evidently there was, some sinkhole down below. Even developed country happening like that, So this thing happened. So during the construction work, you need a good, the control of the displacement and also the waterproofing. Otherwise, you have a lot of, problem. So factors influence on the ground surface, you can report, all the soil properties, so on. And all of this occurred July months, because July, August, there's a monsoon season, a lot of rain comes, okay? They come into the ground. And most of it, detriment, effect, soil line, old soil line, wastewater line. That may be more than 20 years old, 30 years old. Maybe during the excavation, vibration and the losing soil, and then the connection part and lose, So, and the heavy rain comes, water will, seeping down. That create a big problem, we found out here. And another one, rainfall intensity, all the happening in the August or July months, okay? So this is so we got to be very careful. So before rainy season in the spring, we opened the the ditch, and we extracted all the out, garbage out from the sump, okay? So to facilitate water drainage, okay? So that most we got to do. So this is a view of the downtown area. We have like a brown color. That is alluvial sand, So that would be careful, because of higher water table and the loose. And this is a number of I think sinkholes increasing steadily. And we had a problem. We request to the government and the Congress the establishment of underground safety law. So we are good friends of the politician. See, engineer, you are not working. You need something, work with the government and the politician. Put in the, so the law, so we can get a job. Now they acted 2018, government, the make order. If we excavate more than 10 meters, you got a small scale underground safety assessment report. You got to submit to government, okay? So your home is okay, Government will control the safety. But if we have more than 20-meter excavation, heavy report on the assessment of the underground safety. So that this is a real great deal. So we had a lobby, lobby with the Congress, okay, drink a beer or something, Then you have money you're on your hand, So we have it like this. So we have, size of, that's a report, They should include all these data, underground utilities, and also geotechnical data, geological data. This is very important, So we have, no place, right? They like to have a soil investigation. So if you spend more money for soil investigation of what's the ground like, okay? So you're safe, and to save money. This is more important. You need more than 3% total budget, then happy, 1%, somebody say 1%. That's ridiculous, You shouldn't allow that. So like this, gravity stability, stability of underground. This is a chart. Okay, report, you should write one by one, all these follow. Okay, I cannot follow. So that's very important. Okay, they write a district report. Okay, engineer, many young engineers, they should do it, So in South Korea, many companies want to hire young engineer. They don't want to work, for the private company. We'll give you good money, $30,000 or $40,000 per year, but they don't want to work. They want to work for government, and relax, government company. That's too bad, So we don't like it, But anyway, this is important, So you should, negotiate with the parliament, congressmen, and put in the law. And the monitoring, many regulatory, Russia also had a regulatory requirement, right? Or control the safety. And the British also on, we look at it, and the Korean standard. And this is one of the examples I just found before, coming here. This is some 9-story building, and this is Incheon Bay, but we have a coastal line here, right? This is a bay, and if we excavate, what happened? Seawater will come into the basement here, underground. Otherwise, we have a good, water barrier system. So this is one example, like this brace cut. We have a strut and something, and anchoring or slurry wall also. So maybe here somewhere, underground utility, maybe it's very dangerous, because of deep excavation, water seeping out, there maybe has a, some settlement problem, So we check out everything. I'm the one of expertise, and also instrumentation, inclinometer, also the groundwater table, strain gauge, settlement plate, and so on. And these are the monitoring device. And not only this site, also in Jason, next building, we put gauge. You can see during the excavation, we see it. If we deep excavation, we have a monitoring system, automatic monitoring system. There's a red light, yellow light, green light. So the displacement, any the variation below that, the allowable line, green light. But it's a large deformation, maybe some yellow line, warning, and red light, stop construction work, like this, okay? So this is a variation of all the allowable settlement and so on. And this another, 300 or so on, and the box covered on, because this guideline is very important, So we follow this rule, You write the report and the numerical simulation, for the small size of the, the water, the CW, like seepage, and the little large area, the mud flow, ground control, So these are the value we follow, okay? So I can go all detail, tilt meter and so on. And also during the break, excavation, tunneling, sometimes rock resting, boom, like this, boom. So there's a noisy, okay? So some vibration, like we say kind, right? Centimeter per sec, right? So livestock, national treasure building, residential area, but we normally control 0.3 kind centimeter per sec, right? For the shape, like this, okay? Even residential area. And this is a noise level, boom, and then you said big sound, So your baby is crying, right? Your baby is crying, So what do you do? Breast it in the 11 o'clock, okay? 2 times the breast, 11 o'clock or in the afternoon, 3 o'clock. So housewife, so they, husband will go to the company and wash dishes and then go shopping, Wife and go shopping 11 o'clock and 3 o'clock. So we bomb, like this, civil engineer. We are very clever, So like this, okay? So see, this is important. This year alone, for the estimation of the underground safety impact, you see like this, 1,000, cases at the 10 to 19 meter. And another one is greater than 20 meter deep excavation, 200. And then after those, they post like 200 cases. So by the money, So how many people can work there? So geotechnical engineer, very happy, very busy, So you can make a good money out of it. So, but That's extra. Or you want to before construction work, you want to find the sinkhole like this, GPR, okay, GPR, and also the GPR test the additional charge for visual observation, and sometimes you put in the drone. Drone is very common now. Drone survey nowadays. Look around any trace, subsidence or something. Okay, so this is the conclusion, and I think water level is a very important observation. Water level is down very, very quickly. There is something, a sinkhole, hole is exist. But year later or 1 year later, heavy rainy season, they may be all of a sudden collapse. Have a big sinkhole, maybe somebody motorcycle, the guy maybe to look at another place and driving and the collapse, somebody died. That's serious, stupid, that's hole. But he look at this, oh, then die, oh, hallelujah. Like that. Crazy, So that whenever you have a deep excavation, you got to write a report on the assessment of the underground safety impact. Okay, I think this is very good. So protection your private properties and the government, the public sectors of safety. Thank you very much for your pay attention. This is a view of Incheon, downtown. Okay.
Thank you very much, Professor Yeon Chul-shin, for your very interesting presentations. And also, is a very nice view. Sondo city, it is a real new, like similar Astana, like capital there. Is looking, it is Astana or Korea sometime. I am shaking there.
Yeah, we take scepter, Astana area, Astana has a building like this, like this. Wave, we just make a wave. Like
Yes. So thank you. Some questions from auditorium, especially for students, because it is special students you coming,
Sure.
looking new aggressive students, our new generation. Now we must give button to him. Okay, so please. No questions. Very, very clear. So
you're more than welcome to visit, Incheon. There's airports there, I'll accommodate you, one night hotel free of charge,
Yes. Maybe more, not only one night, maybe 1 week is better. So, Professor, so you have many sinkholes. You show many sinkholes, especially in Korea. Many sinkholes now, develop of number of sinkholes. So what is the reason sinkholes? Because, not so many countries has sinkholes. Some very developed country has sinkholes.
No, you see, Japan had a lot of sinkhole about 20 years ago. We had a lot of sinkhole maybe 10 years ago because we don't control the groundwater table level. No, the government should control the groundwater level. So we have, because of a lot of development. You see, we had a lot of metro line, crazy metro line.
Kalashnikov, да?
Yeah, you see, like this. We're digging out everywhere, So 17 underground, metro lines. So there is a waterway underground also. So it's a water path, But the station, some underground is a big structure. So water is coming anyway. They're scouring, So not well compaction and not have a good groundwater control, And all the saline is old, 30 years old. So you need to replace it, saline. I don't know, Kazakhstan, you may have it very soon, Astana area. So we got to replace it, new saline, okay? So we don't control, but it's very good for geotechnical engineer anyway. We're happy, Anything happen, we have a job, something. Anyway.
Thank you very much,
Construction work
Yes.
in downtown Seoul.
Thank you, Professor, so for your interesting presentations. So now we must be moved to another. Okay, one question from our Mодератор, Professor Шулятьев.
Спасибо за очень интересный доклад.
For interesting presentation.
У меня вопрос такой. Значит, вы сказали о том, что была организована специальная комиссия, которая контролирует выполнение работ при подземном строительстве.
Yes.
Как изменилось количество аварийных ситуаций после того, как заработала эта комиссия?
Yes, that's a good question.
The second part, how the number of accidents, creation of this.
That's a good question. We control the Ministry of Transportation and Construction, their authority control the underground safety impact, okay? One is, so the Minister of Construction, they cannot control all, so they give the job to the, we say that public housing and the land development of corporation. That is one agency. And another agency is some national safety control institution. We have a national safety, so infrastructure safety control institution. So two institutions. One of my former student, PhD student, is a director of that second institution. Okay, so they control. So when you have a project to excavation, your building underground, you got to write a report. So who write the report? Geotechnical engineer. We write a report for the client. Okay. So before permission from the local government, the city, to construct it, you got to submit this report to the Ministry of Transportation Construction. So they call the expertise like Professor Shin to review this. So I review some problem, I remark it. So then give it to the client. So they collect it, okay? So I want to have a slurry wall for cutoff or something, some methodology changing it, So then I will return it, I read it again. So this is so safe, I say approve, okay? Approve. Then the government, they allow to construction work. So professor has a big authority, like this. You got to listen. Hello, professor, like this.
Thank you, Professor. Олег, надо уже по времени.
Accident. You see that we had a lot of accident. 2014, 2015, a lot of accident. But nowadays, it's very rare to find the accident. Very reduced, like a pandemic. Pandemic is not collapse.
How much?
Yeah,
How much?
How much? Maybe reduction used to be, let's say, 70%. Now, maybe 20% or 10%. Yeah, reduced.
Okay.
Thank you, Professor. Very good committee work. Thank you. Dear colleagues, so now we move to another our presenter. So next presenter will be Professor Kenjian Shou. We say in our geotechnical community, we say Albert Shou professor. He representative of National Chung Sing University in Taiwan. Also Professor Shou elected new our vice president for Asia International Society after Professor Shin. So Professor Shin team will be finished next year, 1922 in Sydney in May. So after May, our new president will be Albert Shou. And also today, Professor Albert Shou will be make presentations and design of the returning structure for MRT deep excavations in gravelly soil, the experience in Taiwan. So please, Professor Albert Shou.
Yeah, thank you, Professor Askar, for your very gracious introduction. Professor Shin and honorable attendees of this very special event, I would like to say hello to you on behalf of Taiwan Geotechnical Society. As you can see, can you see the slide? I hope that you can see. If you cannot see,
Yes, we can see.
Yeah, okay.
Very nice
as
slide.
You can
very
see,
nice slide.
Yeah, as you can see that the title of the presentation today is back calculation of parameters in the deep excavation case study in Taichung City. Actually, the background of this study is that we are going to build a two high-rise building adjacent to the like a infrastructure connected with the MRT station. As you can see, those two deep excavation is kind of a deep excavation for high-rise building. That's correct. The future scheme of this project is more like a twin tower. The high-rise building will be around 65 stories in the future. The reason for this study is that we have no idea, have no detailed idea about the parameter of the gravelly soil in this area, because even though we have a lot of construction in the 80s, but since the height of those buildings is not so high, so the foundation is only down to about 20 meters below the surface. But since the property is more and more expensive, so the building is higher and higher, these two could be the deepest building in this area. The depth of this foundation is about 37 below surface, 37 meter in deep. And also the groundwater is very high. So it's kind of complicated situation we never experienced. And since the gravelly soil is difficult to quantify the parameters, so we try to use this very special project to do some monitoring job and use the data we collected to do the back analysis in order to obtain the parameters that we can use in the future. So that's the background of this study. As you can see, this study can be separated in two steps. The first step is to do the literature review in order to see what will be the range of the parameters. Although we do have some project done in this area, so we try to collect the data first, and then we try to do the sensitivity analysis and try to match the results analyzed by the numerical analysis with the monitoring data, such that we can have more idea about what would be the data. The numerical model we applied is a Flex 3D, and these are the theory behind that. I think you can easily find that. For the sake of time, I will skip this part. So basically, it can be described as the damage strength part and the anti-tensile strength part. So still, there are a lot of parameters behind this theory. But still, we try to use this model to do the three-dimensional analysis in a very simple way. We use the Moore-Coulomb criterion for the analysis. Since there's a groundwater condition in this site, so we also use the building fluid model. The seepage model is considered, and also the water reduction and the excavation process in this site was simulated by the numerical analysis. In other words, we have a lot of detailed numerical steps to simulate the construction and also the groundwater condition, since we have a dewatering job through the excavation. So the fluid solid coupling model was applied, and the construction steps, support step, and the dewatering step are also simulated by this three-dimensional analysis. So you can see that this is the cross-section of this deep excavation. We have 9 excavation stages and 8 support layers. So we simulate this excavation step by step in 3 dimensions. And this is cross-sections of the meshes we applied. And also for this excavation, we use the 4 casing piles as the retaining structure to provide the support to the excavation slope. And in this figure, you can see we collect the since there's a very detailed monitoring system, we only adopted the data from the location where the data is more reliable. And as I said, the first step is to collect the data from the literature review. So this is the result. This table shows the range of the data for the gravelly soil in this area. So so the first step is try to, but you can see that if we use the average parameters, you can see that the monitoring data and the numerical results is not totally right, especially the maximum horizontal direction displacement is not, there's some discrepancies. So we try to, try to use different friction angle first, and to see which friction angle is more feasible. And then this is the result for different friction angle, different color of the curves, and then we adjust the cohesion in the second stage to try to see which combination of the friction angle and the cohesion can get the results close to the monitoring data. This is the whole idea of the back analysis. So, but the results suggest that the 34 degree with 35% reduction of the cohesion, and the 38 degree with the 95% reduction of the cohesion of the average value can get the closest results. But for the second case, for the 38 degree case, we found that there are some plastic strand appeared in between the casing piles. So I think this is not right, because in the field there's no such behavior appeared. So finally, based on what we analyzed, we suggest that friction angle of 34 degree with the cohesion of around 9,750 Pascal could be the best fit parameters for the future design in this area. Then we use this the data for the other side, because as you remember that we have 2 sides, right? We apply that in the second side to verify it, to see whether it is correct or not. And the results suggest that the maximum number is close to the monitoring data. However, the depth of the largest horizontal displacement is not totally in good, very good agreement. There's some discrepancies. The discussion about the discrepancies can be summarized in 4 points. The soil parameter could be not the same exactly, because this is alluvial formation, and also the geometry of the excavation for the 2 sites are not the same. And the third is the groundwater condition could affect the analysis results. And finally, they might be other main, labor related condition that could affect the results. So I would like to skip this one. Finally, I would like to give you a brief conclusion. The results suggest that the the 34 degree with 35 decreasing of the coefficient could be the best for the data in the analysis in this area. And also the on-site data and test results could be suggested to avoid the, as you remember that for the second site, there's some factors. So the on-site data and test results will be good to clarify these discrepancies. And finally, I think the other factors should also be considered to make sure that the data is more suitable for the specific site. So this is the conclusion. I think that's about it. Thank you for your attention.
So thank you very much, Professor.
Professor Askar, I would like to ask you for your pardon because I have to catch a high-speed train in maybe 5 minutes. So I can only answer one question.
Okay, thank you, because you elected the vice president. So we will try to be only one question, please.
Thank you for you to say that.
Есть вопрос, нет? So thank you, Professor. You very clear made presentation, so no questions. No questions.
Okay, thank you very much.
Thank you.
Okay,
safe trip to you.
Okay, thank you. See you later. Bye.
See you. Sorry, Ankit Garg is here? No? Ankit Garg? No. So next, we move to next presenter. So next presenter, Mario Terceros, Executive Director of Incotec Santa Cruz, Bolivia. So Mario is one of biggest geotechnical piling expert in South America, and especially also not only South America, and also ISSMGE. So he also more work with the piling testing and also checking of quality of pile performing, and also more related with design and monitoring of piles. So also he produced new technology for testing. So now today he will be make presentations, constructions, and testing at the same time, new technologies in deep foundations. So please, Mario.
Thank you very much, Askar, and thank you very much for the invitation and all that are present in this morning. Okay, for us it's very early in the morning, but for others it's in the afternoon. So I hope you have a great day. Okay, I will start sharing my presentation. And what's the idea?
Yes, we see. Very good, very good.
Is clear?
Yes.
Okay. The time we know is not much, so although the presentation is quite long, then I will send this presentation. But what I would like to discuss now is how can we get information while we are constructing the foundations. At the beginning, we know we were using the driven piles, about 2,000 years of it, and since several centuries, the oldest method to get the capacity or the service load of the pile was just counting the block counts versus penetration. And this is still the way we are doing right now, even with very modern equipment and with the pile driving analyzer. But the sophistication, of course, has improved very, very much. So this method is perhaps the most well-known and accurate method to get capacities or service load while constructing. Of course, there are many limitations we know for this technology, but anyway, it was a really big step for the deep foundations. Now we have also a very sophisticated data acquisition systems, but the data acquisition systems are mainly to get information about parameters during the installation and not necessarily to the pile, because, for example, if we measure torque and penetration force while we are installing a full displacement pile, we are measuring the parameters for the tool getting there. But anyway, it's a very, very powerful tool, because then we get the parameters of each single pile, and we can correlate with very few loading tests, and we get a very accurate result. In our recent experience, we installed around 600 piles, and we had all the information with these methods, and then we perform 3 or 4 loading tests, and we cross-correlated, and really the difference were less than 10% according with this system. So as much information as we get, the better we can know about the results. So the question remains: what about when we are installing piles and the information we get is not possible to correlate? For example, if I'm drilling a pile and I will get depth and I will get torque, something like that, but it's very difficult to correlate that with the capacity of the pile unless I perform a loading test. And mainly in drill piles, the problem is the tip. So now we will present 2 technologies that not only improve highly the behavior of the piles, but also allows to know what is happening in the 100% of the pile toes. Oops, I don't know what's happening. Okay. The first is the tip of grouting we call smart cells, which basically, when we know the behavior of a pile, the response of a drill shaft, we know that we have the tip resistance, the friction resistance, and the first problem we find is the non-compatibility between the allowable deformation of the shaft and the tip. So that's a typical curve for shaft and for tip resistance, and we can really know what much we would need to move at the tip in order to get the maximum resistance, or at least the highest possible resistance. But the problem, what is the problem? The problem is that if we don't do something, we are not optimizing the maximum axial resistance, because in general, all the methods really do not produce the best result at the tip. In some cases, we have debris. Even if we clean it, it's very common to have debris at the bottom of the excavation. We have decompression. We have alterations because of the tools we use. So the tip, and in some cases, a couple of years ago, when I was in Taiwan, we were talking with some people that they prefer not to use the tip resistance, mainly in very fine sandy soils on the water table. So, but that's something that we can improve with very few effort indeed. What happens if we grout the tip? Okay, for tip grouting, we can have several methods, from open grouting with 2 manchette, with the flat jacks. But all those methods just give us raw information about the volume and the pressure. But if we don't have confined at the pressure, the problem is that we really don't know accurately where the grout is going. And if we don't have enough deformation of the element, we are not really improving as much as is possibly needed. So what we will present here is a method. It's like a bidirectional cell, but of course not so sophisticated nor so expensive. So we can not only compact and preload the tip of the pile, but also we measure with telltales the movement of this cell. So we are performing a loading test in the 100% of the pile toes, while we are knowing the soil conditions and we are knowing really the resistance of the pile. That's the typical presentation, where we have here ungrouted tip, and here we have a grouted tip. What is happening there? That we are pre-mobilizing, we are pre-deforming the tip. So the pile, when it starts to be loaded, then it has first to overload the preloaded we had. So in that case, we are making a much stiffer pile with a much stiffer response, and with a very important compatibility of the formations for the maximum load of the shaft and the tip. This is just a sketch, but mainly in the smaller to medium deformation, let's say up to 100 millimeters or 150 millimeters, where almost no structure will have this allowable deformation, we can really get a big improvement, because if we move a pile, let's say 30 centimeters, of course it will converge with all the improvement of the bottom soil, but that's not acceptable in any kind of structures. So the question is, why do we perform? The first thing is we optimize design, because with the same pile, exactly the same pile, we can increase the resistance dramatically. In some cases, we have measured up to 100% of improvement of the pile resistance. So, and in that case, the risk is mitigated because we know what will happen. We know for each single pile the behavior. And the scary thing is that in some cases, even for one block, we have a really big variation of response, mainly in very new soils, quaternary soils, close to very new rivers, so where the sediments are really erratic. Knowing that, we have a very high quality control, quality assurance. And of course, if we get a rigid, a stiffer response, we will get cost saving and time saving. In one project with 90 piles, we reduce 6 meters per pile. So it implies that the construction time were significantly smaller, and also the final cost. This is the typical presentation where we have this element. We surround with a geosynthetic because we have a quite of control leaking in order to cement the cell outside of the main body. And here we have more details that how it works is like a bidirectional jack. And the good thing is that we also have, and here I forgot to draw here, we have telltales. So when we move downward the cell, we are knowing also for each pressure, so we can know the force multiplying by the area. We can know the deformation. Here is the general presentation of the cell, what's happening, and you can see that starting from the closed cells up to the open cells, in some cases we can even move upwards the pile. And in some cases we have calculated that the assumed friction or shear resistance was 4 times that the one we measured. So the problem is that in some soils the calculations are very, very far from the reality. So what are we doing? We are premobilizing the tip resistance while stiffening the soil. So we are improving greatly the performance. This is a real case where we started to mobilize the cell. So we had a very low stiffness. This part is always around 20 and 40 millimeters, and we consider it's a debris compaction. Then we start to compact the natural soil here, and at certain point, this compaction is very small because the shaft start to move up. At certain point, the shaft will move without any additional movement at the top, at the bottom. So this is typical bidirectional result. So here we got 3,500, but summing both, we put 7,000 kilonewtons for a pile that was designed to work at 5,000 kilonewtons. So this pile will have only elastic deformation at the moment of the service load. And here we show that those are injections for different piles in the same block. The same here. Here we can see the difference that are much bigger than here. okay, those are not so important to present now. And in a mini case story that a work we finished 3 months ago, we have here the soils, we have all the information, and that's the interesting thing. In a block with 7 piles, those were the injection records. We mobilize up to 40 millimeters, but when we perform the static load test, the maximum mobilization for 900 tons, 9,000 kilonewtons, was only 10 millimeters. So this pile could have resist twice what it was designed for. Okay, some conclusions of this method. As we talked, preload, premobilize, compact soil, optimizing design, stiffening the formation, reduction of post-construction settlements. We can shorten quite much the length. We have also all the analytical method. The FHWA has a very good compilation for this type of designs. We have a reduction in carbon footprint, and of course the compatibility of the formations. The other method that will be fast as possible is expanded body, which basically is a steel balloon that you install at the bottom of a pile or of an anchor, and once there is expanded by injection of grout. So we pass from 12 centimeters, in some cases up to 1,200 centimeters, 1.2 meters. Typically, we use between 600 and 800 millimeters in diameter. And okay, here are the models. And what are the advantages? We can have a very important cost reduction. The time reduction is great because if we double the capacity of the pile, then we diminish the quantity of piles to be done. And we can know with a curve that I will show the behavior of the soil like a pressurometric test. We have used even in one case in very soft rock, not to mobilize the rock, but to get a very high shear resistance between the rock and the element. Of course, the limitations for low loads is not an advantage because you get always high resistance, and typically the shaft should be less than 1 meter. So the maximum loads we have get in service loads are around 5,000 kilonewtons, but that's for many buildings is more than sufficient. Because we have blocks. In one case, we had a block of 200 piles of 300 tons each one. It can be used in almost any kind of installation method, even in very reduced areas, because the element itself is very small, and you can install with pipes or in drill piles or with vibrator-driven piles. Also, each element has a calibration curve, and that's important because in case we have a puncture or whatever, we know with the measured volume what is the real diameter, and we can calculate the resistance with the real diameter and the pressure. Those are typical cases of 2 elements installed, one in a full displacement pile, so you see that the initial response was very stiff, another in a drill pile, deeper than the other, but with a softer side resistance until it gets up to the limit pressure. We also provide a post-grouting because in soft soils, it helps to reduce settlements. And it works like a pressurometer, and that's why we get the typical injection curve, which is very similar, but this is a very high deformation pressurometer. We have performed several tests, loading tests, and correlate with different elements with CPT, SPT, pressurometer, and other methods. So as we get very much information from each pile, the correlation with the loading test is much more accurate. Okay, here are typical method of calculation. The method based in pressurometer is perhaps the most accurate one, but we have also made correlation with SPT. I don't like it, but it's the problem that in South America is a very common test, and we use a lot of CPTU. This method has been also calibrated for the local soils, because as we, the engineer, we also have a parameter that varies from 1.9 to 4.5. So if we don't get a good calibration, it's kind of crazy. But now we have installed more than 30,000 around the world, and it really works. What happened if I had a loss of pressure? Then we know in which pressure and which volume we can calculate. All those are real curves. This is a very soft sand. And at the end, all goes to the critical condition because the concept is that the shear is fully mobilized around the element. This is a very nice comparison. We install a micropile without expanded body and then a one with expanded body. Here you can see 6-7 times more. Of course, that's on purpose because it's very impressive. This is a typical one where we have a drill pile. And we got for 50 millimeters more than twice the resistance. And this was a resume of different piles without any kind of tip improvement and with expanded body or full displacement piles. This is a case that those buildings were finished 6 months ago. This is a big project with more than 800 piles. And in that case, we have saved 63% of the volume of concrete, the same in steel, and in time, and in cost, because as we can, with higher quality, concrete quality, of course, that is cheaper and faster, much faster. Conclusions, okay. Reduction, high quality of installation and control, and we also get this, that's very important. We are very keen always in the formation compatibility, because many methods say that for the shaft resistance, you will use, I don't know, whatever of safety factor, which is not true, because after 6, 7, 10 millimeters, you have mobilized the full of the shaft resistance before starting even to mobilize, in some cases, the tip resistance. And in this case, the carbon footprints, we have calculated savings up to 45% compared with traditional methods. Okay, this is our board of advisors. We have very good friends, and they like very much the method, so they are always keen to offer more information about these systems. And here, in this QR, we have publication and reference. So you can get, we have several publications, not only for us, but made by other people. So please, if you have any question, I really thank you very much. I thank the organization, and I hope we can be useful for the industry. For us, even in very poor countries like Bolivia, we have been very successful and very competitive. Now we have installed, even in Canada, United States, we have finished a project in Boston 2 months ago, in Brazil, Peru, Argentina, Paraguay, Bolivia, and we are starting a project in Chile too. So please do not hesitate to.
Thank you, Professor. Thank you, Mario, for very interesting presentations. So please, it is a real, very interesting presentations with some experience and also some real results and some real realizations of his methodics, especially in construction site. Because I visited one time Bolivia and I visited construction site. I look of this construction, especially testing activity. It is very impressive there. So please, some questions from auditorium.
Можно?
Да, yes. Professor Шулятьев.
Thank you very much for good report and very interesting. But my questions about the material of body, expanded body, and smart.
Yeah.
What kind of material?
Yeah, both are steels. In the smart cell, is a steel that is thinner than the typical bidirectional jack. And in the expanded body is a special steel of 1 millimeter thick that allows more than 40% of plastic deformation because breaking. And that is very important because the folding, if not, they will crack. With regular steel, it cracks. So we have measured in real cases that the plastic deformation we have got were about 20% of the total length. So this is one of the important points, and the compatibility between the weldings and the deformation of the steel plate. But everything is of steel, and the steel in the expanded body is intended to get roasted because it's a very thin, and it's just a container. It has no structural use when the body is working. It's like creating a rock wherever we want, compacting the soil. And you can imagine that if we compact for let's say, one short example, a typical expanded body has a 2 square meters of surface, and when we inject with a quite small pressure, like 2 megapascals, we are talking about 200 tons per square meter. So in 2 square meters, we are putting 400 tons of force into the soil. And that's why we can move the soil. And the effect of compaction, we have measured up to 6 diameters, some effect of the compaction. And that's why after the installation of the piles, the density of the soil has increased around 10%, which means that you pass from a soft sand, loose sand, to a very dense sand. So that the benefit is not only punctual, but also in the groups, the big groups, because you are creating like a very rigid slab of soil.
Thank you. And second question is, what should you think about the use with technology for Ankor?
For some, sorry, I didn't hear.
For Ankor.
For Ankor, yes, we have a lot of experience in Ankors, and
Ankor,
typically
yes.
It was invented for Ankors indeed. And in Ankors, the big advantage is that not only increase very much the resistance, because instead of a cylindric extraction element, you have a cone extraction element. And in Ankors, in the other method, if you follow moving it, at some point it will fail. But in the expanded body, you are compacting the soil. The more you move, the more you compact. And in some cases, we have re-stressed the Ankors 2 months later, and we have increased the resistance very, very much. So for Ankors, it's a great solution. We have installed in the Vancouver area in Canada Ankors where all the other methods fail, and in very, very soft clays, they were with, if I'm wrong, around 30 kilopascals of shear resistance, and we could get the loads quite easily with quite much movement, of course, but at the end it was working. So for the Ankors, it's a great solution. You can reduce the length, which means less drilling, and it's very fast. And you know, the most important thing is that you know what is happening in each single element. You are measuring it.
Thank you very much.
So thank you, Mario. It is very interesting presentation. So you already showed for us your email and mobile telephone. So I think is our participants already made copy. So we will discuss with you in future by email. Okay?
Sure. And thank you very much, Askar.
Thank you. Thank you very much. And have a nice day. Have a nice day.
Thank you. Same for you.
Thank you. And now we move to my presentation. Oleg, some presentation.
Уважаемые коллеги, следующую презентацию подготовил наш дорогой модератор Аскар Жагпарович Жусупбеков. В настоящее время он является профессором и в то же время директором или генеральным директором геотехнической ассоциации Казахстана. Пожалуйста, Аскар Жагпарович.
Спасибо, Олег Александрович. So thank you very much for Dr. Шулятьев for giving to me opportunity speaking, especially in Moscow State Civil Engineering University. So I think young generation know very well English, so no problem there. And also we have already inside of this screen, we have several foreign participants. several foreign guests, so maybe better speak by English there. So my presentations more related with comparative analysis of static and dynamic pile test in the difficult soil of Kazakhstan. So I have also my colleagues, Askar and Doctor PhD students from Gumileva Eurasian National University in Nur-Sultan. My co-author, Dmitry Yuryevich Chunюk, Doctor PhD from National Research University of Moscow State University of Civil Engineering. As usually, he is my boss there. I am work here like professor of part-time professor of Department of Geotechnical Engineering of Moscow State University. So very thank you for joining with us, my boss. Thank you. So you know, these contents related with the site investigations and the site testing in Nur-Sultan, site in Petropavlovsk, so dynamic pile test in Nur-Sultan and also Petropavlovsk. So you can see this Petropavlovsk is also Russian name there. So Kazakhstan is very nationality, internationality people. No change, Russian name to Kazakh, no problem. So static pile test in Nur-Sultan, also again static pile test in Petropavlovsk. In conclusion, so this is more related with hospitals. So now you know it's pandemic, press it of and press continuously to press of world populations. So now we made and also make several new modern hospitals in Kazakhstan. So this site in Nur-Sultan, so you can see this 800-bed Astana Medical University Hospital. So this is constructed in the right side of right coast of Ishim River, city Nur-Sultan. So this is you can see this total area of hospital more than 100,000 square meters, very big hospital. And also you can see this is several facilities included several beds for cases, people. And you can see this is very nice picture about his architecture design from a company from design company from Turkey, because this hospital more clients and are clients from Turkey, because already Turkish this company has many experience in the world. So this is site of in Petropavlovsk. So this is also you can see this is a little bit small because it is not so big city like Nur-Sultan. So about maybe 540 beds. So this is also very interesting projects because in Petropavlovsk soil ground is different than Nur-Sultan. So this is dynamic pile test in Nur-Sultan. So this is dynamic pile test in Nur-Sultan. You can see, especially for young generation, may be interesting because we use a Yunton machine, very new, very interesting technology with hydraulic hammer. Because before in Soviet Union time and after collapse of Soviet Union, we use more in Russian diesel hammer. But diesel hammer cannot penetrate and drive of piles and driving piles into soil ground before design level because not so enough weight of hammer and also not enough frequency of hammer. And also sometimes, you know, it depends from soil ground. So frequency not changing and he destroy of top of piles. And also productivity not so big for comparison this Yunton machine. So Yunton machine can drive for comparison 150 piles per day, same size. In Russian hammer only 15 or 30 piles per day. So you can see for young generation, you must thinking not about small price of machine. You must be thinking about in future productivity machines. And also you can see these machines can work also very well in winter time, also very well, not only autumn and summertime. So this you can see this number of piles. We make some dynamic tests. And this is dynamic pile test results. You can see this is bearing capacity around 81 ton. And you can see this date of testing and also the parameter of pilings, the length about between 10 and 12 meter in Nur-Sultan. And cross sections is 30 to 30 centimeter. So this dynamic pile test in Petropavlovsk. So you can see this also we carried out of our test in the winter time. So Yunton, we use of Yunton PM25. So also you can see several piles between 1 and 17. So this way want to understand of drivability of soils for our machines in our piles. So you can see dynamic test of petropals. Petropals about 74 tons. And also we use more 12 and 13 meter because in petropals more soft soil for comparison in Nur-Sultan. But in the sections of cross sections is 30 to 30 centimeters. So this some in Nur-Sultan you can see we use about the depth of piles about 8.5, about 9 meter finally. And then Petropavlovsk, you can see we use more about 11 meter. And but anyways, the piling and finally we using of our safety factor, we receive about 58 ton. For Petropavlovsk around maybe 53 ton. So this is a static test for Nur-Sultan because our client was Turkish company. If it is not Turkish, we usually use only dynamic test. But Turkish company request us also making also static test. So for the static test, you can see, so we made in our special standard. It is maybe Russian standard and Kazakhstan standard is similar. So with jack, with testing beam, etc., etc. So this static pile in Nur-Sultan, you can see this testing pile inside of slide piling map. So you can see static pile results. So we also make loading and unloading, and received is about bearing capacity between 78 ton and until 90 ton. So this static piling test in Petropavlovsk. So this is a test made our PhD students. It's very easy for PhD students. Also he received good salary and also make researching and also some experience there. It's very interesting combination there between research, education, and also business there, So because we send our students sometimes abroad for international conference, so need some travel money. So this is static test for Petropavlovsk city. Also we have same methodics, loading and unloading. So we made test until 40 millimeters the settlement regarding our standard. It is similar of Russia standard. So summary of static test results for Petropavlovsk city. So finally, I move to conclusions because time is really extremely going well. So we dynamic and static test very important, but very important dynamic test only for understand drivability. For drivability, because we know in the left side and the right side of piling map. So we want the central side. So we understand how this pile can drive into soil ground, driving. And also we need to understand this dynamic bearing capacity. But in reality, especially for foreign company, also very carefully ask also static test. So we made about minimum our standard 6 dynamic test and also minimum 2 static tests. But a foreign company about 2 times more dynamic test number and also about 2 times more also static test number. But anyway, bearing capacity of determined by dynamic test is approximately about 12%, about sometimes 15% lower than during of static pile test results. So we have also, already I told about 17 Asian Regional Conference, which will be held in the August 2023 in Kazakhstan. So I want try also invite you for this conference. So conference will be 16 and 18 August 2023 in Astana. So conference venue will be Expo Congress Hall in Nur-Sultan. So anyway, we invite also young generation because during time of this conference will be also some seminar or workshop or related with young generations, because also young generation very important. Also, we will have some sections for industrial companies who cannot speak English. So we will organize some sections by simultaneous translations. for this group. So it will be some also very interesting maybe for industrial people. So no problem. So language, no problem. In Kazakhstan, we very like Russian language, no problem. So you can good communicate with Kazakh people, also by English with foreigner. Thank you for your attention. So this is our professor. Thank you for yesterday supporting. You can see, so tomorrow, after tomorrow, we will move to St. Petersburg. So St. Petersburg, we will be also another conference with participation Professor Shin. So Professor Shin will be awarded for honorary doctor of St. Petersburg State University. So he has 2 awarding ceremony in the Russia. So thank you for your attention.
Thank you very much for your report. And I see the Professor Shin is very young. More younger the time go, but Professor Shin younger and younger and younger. Thank you very much. And пожалуйста, есть ли вопросы? What about questions for our very interesting report of Askar Жусупбеков? For start my questions. Я скажу по-русски. Скажите, вот у нас, когда была совместная встреча вместе с американскими коллегами, нам рассказывали о том, что в международных нормах вводятся различные коэффициенты надежности для того, каким способом определяли сваи. Причем сваи можно и рассчитывать, и использовать динамические методы, и сейсмоакустические методы, и статические методы. Но разница составляет в том, что вводятся различные коэффициенты надежности, причем они могут отличаться в несколько раз. Вот в Казахстане перешли на вот эту систему международную определения несущей способности сваи или продолжают использовать все-таки российские нормы, в которых основной является, конечно, статические испытания свай?
Спасибо. Очень интересный вопрос. Thank you very much for your very interesting questions. So, я, наверное, продолжу все-таки по-русски, а вернее по-английски, да, потому что там у нас сидят на экране в компьютере там иностранные гости, да, из Японии.
Но лучше по-русски, потому что они не слышали мой вопрос.
Я потом переведу. Да.
Переведи, хорошо.
Да. So, сначала по-русски, потом по-английски. Значит, очень спасибо за интересный вопрос. Действительно, на российско-американском воркшопе в Сан-Франциско и в Москве, в Санкт-Петербурге поднимался этот вопрос. Действительно, вот это вот, если сравнить все страны Европы, сравнить американские, сравнить наш Советский Союз бывший, то у всех разные коэффициенты надежности. У всех разные коэффициенты надежности. Если, допустим, взять Японию, Америку или Германию, то у них коэффициент надежности примерно 2-2,5 для статических испытаний. Для динамических еще больше, 3, там, 3,5. Если взять, допустим, наши нормы, советские или там российские, или там казахские, то у нас где-то примерно уходит на динамику 1,5, на статику примерно коэффициент 1,2. Если взять, допустим, сейчас вот мы перешли на еврокод, но зависит от клиента, какой клиент, какой заказчик. Если у нас заказчик иностранный, то мы, конечно, работаем по еврокоду. Если все-таки к нам попадает заказчик, все-таки наши российские или казахстанские компании, то мы все-таки на испытаниях применяем наш стандарт. Но я хотел сказать следующее, что это, знаете, вот зависит, вот это вот подача нагрузки на сваю зависит больше не от стандарта, больше зависит от заказчика. Если заказчик дает ту нагрузку, то мы выполняем ту нагрузку. Понятно, да? А заказчик старается дать небольшую нагрузку, потому что это зависит от времени испытания, зависит от возможности вот этой испытательной кампании, от размера вот этих баллов испытательных и домкратов и так далее. То есть старается в очень скоростном режиме все сделать. Если все делать по еврокоду, то это будет очень долго все, потому что коэффициенты у них очень большие и нужны очень большие испытательная техника должна быть очень такая мощная по сравнению с тем, что имеется в наших испытательных организациях. I won't say so. It is depends of client. If client say we must be use of Eurocode or American standard, we use American standard because international company. If it is national or CIS countries clients, we will follow our standard. But anyway, it is different story each test because we have several safety factors on different countries. So, but in our country, Kazakhstan, we now try use parallel of Eurocode and also in our Kazakhstan standard.
Правильно ли я понял, что заказчик стремится как можно меньше дать нагрузку на сваю в процессе испытаний?
Yes, это зависит, эта нагрузка зависит от проектной нагрузки.
От проектной нагрузки.
От проектной нагрузки,
да, я понял. То есть мы в процессе испытаний не стремимся определить максимальную несущую способность свай,
связываемся с проектной нагрузкой, которую дает нам заказчик. Техническое задание.
То есть практически может получиться такая ситуация, что фактически свай может нести нагрузку в 2-3 раза больше, но мы базируемся только на расчетах, которые дал заказчик и проектировщик.
Да, потому что мы не можем перепрыгнуть заказчика, потому что заказчик есть заказчик. Мы не можем пойти против заказчика.
Но это же не экономично и не гуманно. Значит, использовать 3-4 раза больше свай, чем можно было бы использовать в соответствии с их максимальной несущей способностью.
Вы абсолютно правы, Я думаю, что эта история повторяется не только в России, не только в Казахстане, но и в России, как вот вы вчера докладывали или позавчера, что очень большие коэффициенты запаса, да, и получается, что можно было применить в 2-3 раза меньше свай по сравнению с тем, что есть. Но заказчик есть заказчик, поэтому это не научно-исследовательская работа.
У нас
это
есть
идет
как бы корректировка проекта по результатам статических испытаний, повторный вход в экспертизу, то есть это практикуется.
Да, у нас уже практикуется.
Да, это практикуется, но я вам приведу конкретный пример с одной из организаций, которая занимается как раз изготовлением бурно-набивных свай, и, в общем-то, вопрос был такой к ним. Они говорят, что мы сколько свай испытывали, все время у нас получается нормальная несущая способность. А я говорю, а как вы определяете нагрузку, когда проводите испытания? Они говорят, что мы в соответствии с нормами, ну это в частности для строительства мостов, железных дорог, в соответствии с нормами мы должны посчитать по СП-24, а потом умножить на коэффициент 1,5. И всегда, говорит, у нас прекрасные значения. Я говорю, какие перемещения при этом происходят? Перемещения небольшие, 3-5 миллиметров. То есть явно, что, в общем-то, здесь, и это мы знаем все, что наши нормы для бурно-набивных свай дают сильно заниженные расчетные значения. Особенно это касается твердых глинистых грунтов. Но об этом как раз будет следующий доклад.
Да. Я вот хотел сказать, что следующий, особенно для молодого поколения, действительно, вот правильно сказал Дмитрий Юрьевич, что после получения проектных данных, после получения свайного поля, вы проводите обязательные испытания в любом случае. И по этим испытаниям вы проводите корректировку свая. Так что у вас есть, видите, какой запас еще надежности. Вы делаете изыскание. После изыскания вы отдаете эти данные проектировщику. Проектировщики делают свайное поле, рабочий свай уже, да, как бы дает поле. Вы эти рабочие сваи потом еще корректируете испытаниями. Потом отдаете обратно проектировщику и уже получаете реальное свайное поле. И вот это в реальном свайном поле обязательно вот идет испытание, особенно если иностранные заказчики. Вот наши заказчики, к сожалению, уже начинают биться со скоростью и уже рабочие сваи не испытывают. Если испытывают только лишь, когда есть спорные моменты, что она недобита или, наоборот, перебита, сильно быстро зашла. То есть есть такие нюансы, да. We told about discussions about correction of piles after designing. So after designing, we give to testing for pile testing, and after pile testing, we correct our piling map, and after that, we give to construction company for make construction performing of piles. So thank you for your attention. So next presentation will be, может говорить уже, да? Или вы представите, Дмитрий Юрьевич? Давайте, представляйте. So thank you, Professor Hasegawa, for very interesting questions. Because only now I show these few questions. Yes, we usually use we try to use more static results, of course, because static results is more right results than dynamic test results. So dynamic test is not so big high-rise buildings, maybe 5-story, 6-story, and sometimes 9-story. But if is more than 9-story building, high-rise building, we more use, of course, in our bridge construction, we use only static results. So dynamic results only for understand piling drivability, not for maybe for designing of bearing capacity. Thank you for your questions.
So dear Askar, so I think I think soil and rocks will be the show the difference performance for the dynamic and static, I think. So I wonder which is useful for the design of the pile design, I think.
So we, of course, yes, you're right. It depends from soil, and also we use of dynamic test only for driving piles, because for boring piles we only static test. We cannot make driving. Maybe Mario can recommend the new methods, revolution, but before today we only for static test. But of course, if soil ground we have some rock, of course we cannot use also for driving piles, more boring foundations.
Okay, thank you.
Thank you, Professor Akira Hasegawa, for your questions. International questions important also. Thank you.
Okay.
Thank you.
International report, yes.
Следующий докладчик у нас Шулятьев Олег Александрович, заместитель директора института НИУ имени Герсиванова по научной работе. Тема доклада – испытание грунта буронабивной сваи путем приложения двунаправленной нагрузки с помощью опускного домкрата.
Добрый день, коллеги, еще раз. Мы с вами уже целый день здесь проводим. И знаменательно, что последние 5 докладов у нас по свайным фундаментам. И мы будем рассматривать сейчас вопросы. То есть у нас стала как бы секция по свайным фундаментам. Да, конечно, пришла геотехника. Да. Вот. Мой доклад по поводу испытания буронабивных свай путем приложения двунаправленной нагрузки с помощью опускного домкрата. Значит, мы рассмотрим методику проведения испытания, но я думаю, что многие из вас знают, поэтому я кратко остановлюсь. Какие параметры контролируются, и самое главное, мы рассмотрим с вами результаты, которые были получены в процессе в последнее время в результате таких испытаний. Методика проведения испытаний заключается в том, что не нужно возводить большие конструкции сверху, сваи, а сама свая является опорой для проведения испытания. То есть верхняя часть сваи сопротивляется в процессе испытания нижней части. Здесь вот видите, для этого закладываются домкраты и проводятся испытания. Домкраты могут быть в 2 уровнях, и это лучше всего располагать их в 2 уровнях. Здесь мы можем провести испытание нижней части сваи, можем провести испытание средней части сваи, давая нагрузку вот с помощью этого верхнего домкрата. Получить одновременно сопротивление по нижнему концу и по боковой поверхности. Для чего проводятся испытания свай? Ну, такие буронабивные сваи, как правило, устраиваются у нас, и мы рассматриваем в первую очередь это фундаменты высотных зданий. И там, как правило, поле свай. А когда у нас есть поле свай, тогда нас не интересует несущая способность одиночной сваи. нас интересует совместно работы сваи с грунтом и взаимодействие сваи между собой. Поэтому возникает необходимость решать задачу не несущей сваи, а первое – это апробация расчетной модели, уточнение механических характеристик грунта путем обратных расчетов, ну и в какой-то степени определить сопротивление грунта по боковой поверхности и по нижнему концу. Для этого, кроме домкратов, сваи оборудуются еще системой датчиков, для того, чтобы мы могли по результатам решить обратную задачу и определить все эти параметры. Одно из первых испытаний, которое было проведено практически уже 15 лет назад на Москва-Сити на 11-м участке, вот по такой схеме, была свая, вот она здесь показана, которая имела домкрат 1 и раз, два, три уровня датчиков. Справа показаны результаты испытания этих свай, этой сваи. Это перемещение верхнего домкрата, это перемещение нижнего домкрата. Точки – это результаты экспериментальных данных, а линии – это результаты расчетов. Было проведено большое количество расчетов, больше 200, менялись параметры, ЦФИ, модуль деформации, для того, чтобы получить более-менее похожую картину. И что же в конце концов было получено? Было получено, что параметры грунта, которые мы определили вот таким вот обратным расчетом, в частности модуль деформации, в 2-3 раза больше, чем тот, который мы взяли в процессе инженерно-геологических изысканий. Это как бы первое. И второе, что, в общем-то, непонятно, зачем вообще мы сделали такие глубокие сваи в скальном грунте. Это Москва-Сити, глубина котлована была порядка 30 метров от поверхности, и проводились испытания, выполнялись вот такие сваи практически 25 метров длиной. Значит, дело в том, что в соответствии с российскими нормами расчеты проводились по нижнему концу сваи, поэтому искали, где на нижнем конце у нас более прочные грунты для того, чтобы воспринять нагрузку 2-3 тысячи тонн. Ну вот результаты испытаний, это вот показали датчики. Видите? Вот это перемещение датчика, который на первом уровне, который находится на вот это в самом низу, 1,5 метра, а ниже домкрата. И здесь у нас уже на 1,5-метровой дистанции, здесь 220 меганьютонов нагрузка, а здесь нагрузка всего 12. То есть 10 раз практически уменьшилась. С 1,5 метра восприняла вот эту нагрузку, которую мы приложили. Значит, дальше у нас датчик расположен, вот этот второй расположен на расстоянии порядка 6 метров, по-моему. Тут увидите уже всего там 3 меганьютона из 25, которые на домкрате есть. То есть очень хорошее сопротивление по боковой поверхности скальных грунтов. Ну, вот это, кстати, об скальных грунтах будет следующий доклад, поэтому я здесь кратко остановлюсь. Только скажу, что действительно 2 таких момента было получено в результате первых испытаний. Значит, что нужно, какие измерения необходимо выполнять? Первое – это определение усилий в стволе сваи. В каждом сечении закладывается по 4, как правило, датчика. Второе, значит, измерение расстояния между пластинами домкратов с помощью специальных датчиков, которые называются экстензометры. Третье – это перемещение отдельных частей свай с использованием независимо перемещаемых стержней, устанавливаемых в трубе, то есть по системе стержень в трубе. Ну, это все понятно. Вот эти 3 первых пункта нужны для того, чтобы измерять перемещение и контролировать их, потому что должны быть параметры, которые контролируют друг друга. И четвертое, что очень важно, что, как правило, не выполняется, это перемещение реперной балки. То есть балки, к которой крепятся все датчики. И в том числе перемещение самой сваи. Вот здесь видите, как перемещать. Черным показано это перемещение реперной балки. В процессе достаточно долго проводились испытания. Видите, вот тут несколько, 2 недели, по-моему, они шли. Значит, изменялась температура. Фиолетовым показано изменение температуры. Вот как изменялось перемещение балки. Это все фиксировалось с помощью специального прибора, который, ну, типа нивелира, да, тахиометра, который стоял и постоянно замерял, в постоянном режиме замерял перемещение балки. Причем вот тут балка находилась под специальным тендом, и там старалась поддерживаться постоянная температура. Это говорит о том, что очень важно еще контролировать и перемещение балки, и балка должна быть изолирована от температур, от различных показаний, потому что вот эти вот, здесь видите, миллиметры, да, показаны, изменения от температуры 3-4 миллиметра. Ну что такое 3-4 миллиметра, когда точность измерений, которую мы предъявляем, 0,1 миллиметра. И дальше мы должны прикладывать, причем это 0,1 изменение в течение там, 2 часов. Какие же интересные, уникальные результаты были получены в процессе вот внедрения этой технологии, применения этой технологии. Ну, она уже, эта технология не российская, эта технология была разработана Стербергом, она во всем мире применяется, но вот в России в результате применения этой технологии были получены следующие результаты, очень важные для России, для российских норм. Первое – это уточнение механических характеристик грунта по результатам обратных расчетов. То есть мы уже прямо непосредственно в грунте проводим исследования, не доставая образец на поверхность, не обрабатывая его, не создавая снова напряженное состояние, новое напряженное состояние, начальное напряженное состояние, которое в образце, которое в грунте было, а там непосредственно проводим испытания. И вот в результате этого нам удалось увеличить несущую, ну, характеристики грунта и, естественно, несущую способность сваи уточнить параметры грунта. Следующее. Увеличение сопротивления грунта по боковой поверхности в результате нагружения соседних. Определение сопротивления грунта сдвигу по боковой поверхности. Я быстро читаю, потому что сейчас будет пояснение. Переход от свай стоек к висячим и определение параметров ползучести грунта. Значит, вот то, что касается уточнения параметров грунта, я уже вам сказал, это на Москва-Сити, сейчас не буду повторяться. Значит, специально были проведены исследования, испытания на Хмат-Тауэр. Причем сваи здесь испытывались как с помощью опусты и домкратов. По ним мы определили параметры грунта, а потом решили посчитать, сколько же сваи будет нести с этими параметрами грунта и сравнить результаты испытаний других уже свай, которые были изготовлены на поверхности и были испытаны для того, чтобы задать нагрузку на глубине. Видите, сваи были обмотаны специальным полиэтиленовым мешком для того, чтобы снять сопротивление по боковой поверхности. В результате проведенных испытаний было получено график зависимости нагрузки осадки и были получены данные по усилиям, которые возникают в этих сваях. По результатам расчетов, которые были выполнены, первоначально по инженерно-геологическим изысканиям у нас модуль деформации составлял, видите, 66, 53, 92, 98, а по результатам обратных расчетов практически в 2-3 раза больше, чем по инженерно-геологическим исследованиям. Вот эти вот данные, которые мы получили по модулю деформации и по ЦФИ, мы вставили в расчет и сравнили результаты расчета сваи с результатом испытаний сваи, которые вот мы мотали специальным чехлом для того, чтобы снять горизонтальные нагрузки. И получили, что близкие получились данные с результатами расчета по новым характеристикам. Если сравнивать результаты расчета по характеристикам, которые были даны в процессе инженерно-геологических изысканий, то разница составляла 2-3 раза. А вот это, кстати, в углу, видите, башня, это вот башня Ахмат Тауэр, как сторожевая башня, значит, чеченская сторожевая башня. Но пока строительство заморожено и строительство не ведется. Были проведены в процессе лактоцентра, мы смогли убедить заказчика, это «Газпром», убедить заказчика, чтобы он провел одновременно испытание 3 барет. И что мы получили? Мы получили, что вот это вот красное, это вторая барета, вот эта вторая барета, которая находится между 2 барет. Сопротивление по боковой поверхности второй бареты значительно больше, чем соседних B1 и B3. Это произошло за счет того, что при нагружении барет у нас происходит изменение напряженно-деформированного состояния в массиве грунта, увеличиваются вертикальные напряжения и соответствующим образом увеличиваются горизонтальные напряжения. При увеличении горизонтальных напряжений у нас увеличивается, соответственно, и несущая способность сваи бареты по боковой поверхности. Значит, были проведены большое количество вот таких вот испытаний в разных грунтах. Вы здесь видите, это воскресенские, венские глины, юрские глины, марены Загорской ГАЭС. И выполнены расчеты по разным формулам, по разным способам. Вот здесь видите, обращаю ваше внимание. 3 – это расчет по таблице СП-24. 3 – это вот это значение, да? А это экспериментальные значения. Видите, какая большая разница. То есть разница составляет практически 3-4 раза. Вот то, что мы как раз обсуждали на прошлом докладе. Да? Мы берем, вот считаем по СП-24, получаем вот это значение, да? Умножаем на коэффициент 1,5, проводим испытания, получаем, значит, несущую способность, а на самом деле можно было вместо одной сделать 2 или 3. Вернее, вместо 2-3 можно было сделать одну буронабивную сваю. То есть вот это инструмент, который позволяет всем, кто думает, который считает, который понимает все эти процессы, получить экономию. Не знаю, как это удастся уговорить заказчика получить какие-то деньги, но, в общем-то, здесь это уже вопрос другой. Значит, очень важно то, что у нас в нормах для скальных грунтов и для твердых глинистых грунтов говорится о том, что мы должны учитывать сопротивление по нижнему концу. Испытания, которые были проведены по нижнему концу, показали, что да, действительно, нижний конец вступает в работу, но для того, чтобы он вступил в работу, должны быть достаточно большие перемещения. Вот это вот испытания, которые были сделаны барет и свай на лактоцентре. Видите, практически при 10 миллиметрах у нас максимальное сопротивление по боковой поверхности. Смотрим, что здесь, по нижнему концу. По нижнему концу при этих 10 миллиметрах у нас получается всего-навсего мы достигли, ну я не знаю, там 10-й или 20-й части возможной несущей способности по нижнему концу. Поэтому, и причем это все неоднородно, это все не точно, и во всех сейчас расчетах, которые мы выполняем, без специальной подготовки, которые вот докладывали докладчики предыдущие, значит, без специальной, Антонио, по-моему, докладывал, очень интересный доклад был по подготовке с помощью смарт-камеры. Вот, значит, без подготовки или какой-то инъекции дополнительной, значит, мы не принимаем вообще в расчет сопротивление по нижнему концу. Это глинистые грунты. Такая ситуация у нас и по скальным грунтам. Вот слева картинка показана в скальных грунтах. Вроде бы скала не сопротивляется и должна быть большая несущая способность по нижнему концу. Но видите, при каком большом значении осадки это все достигается. А это вот сопротивление по боковой поверхности. Ну, про скальные грунты будет отдельно следующий доклад. Ну и последнее, это то, что касается определения ползучести грунта. Значит, мы, как правило, проводим испытания. В соответствии с нашими нормативными документами это 0,1 мм в час должны быть стабилизации. Мы дальше заканчиваем проведение испытания. В соответствии с английскими нормами это 0,25 мм в час. А мы на лактоцентре взяли и продолжили исследование нижней части барет. И видите, куда еще дополнительно в результате ползучести ушли осадки. То есть очень важный фактор, который необходимо учитывать в процессе проектирования, в процессе расчета фундаментов высотных зданий, по крайней мере, это вот ползучесть. И вот эти данные как раз позволяют нам в натуре получить значение ползучести. Мы сравнивали значение ползучести, которые получили вот таким вот полевым способом с лабораторными исследованиями в процессе компрессионных стандартных испытаний по нашим нормам. Получилось, что здесь у нас эти значения значительно меньше, там в 3-4 раза. Ну, в общем-то, вот все, что я вам хотел рассказать. Спасибо за внимание.
Да, спасибо большое, Олег Александрович, очень интересный доклад. Я думаю, что будут вопросы, потому что все-таки очень такой интересный, реальный доклад. И я думаю, yes, профессор Шин.
Yeah, I have a question. You conducted the OCEL test for the very deep foundation. The OCEL test, you utilizing the American OCEL test, or you developed your own OCEL testing method in Russia?
Да, значит, ну я отвечу по-русски. На английском. OCEL test the same as America and Russia, not difference.
Questions like this, Oleg, questions like this. So OCEL test, it is American standard, or you use some Russian patent?
OCEL test for OCEL test have patent Osterberg from America. Americanский.
Because
patent American.
in South Korea, we developed our own OCEL method, like a biaxial OCEL method. So maybe we use this. Some people they use oil, hydraulic oil, and some people use the water. So we developed our own biaxial OCEL testing method, and we don't say OCEL, biaxial largest diameter biaxial test, and then loading test equipment. So OCEL company in the United States has a battle sue Korean company, but the result, Korean companies won. So patent cannot keep because we modified it. So there's no conflict, you know. So if you pay big money to the American company, you know, OCEL test, you may develop your own, you know, Russian version of OCEL test. So that's what I'm suggesting.
Олег, понял, да?
Yes, of course, yes. For OCEL test, the test provide all the American, not American, English companies, the special English company for have the patent for OCEL test, not Russian company.
His questions, он спрашивает, что у них в Южной Корее тоже есть OCEL тест, но это ихний патент корейский. И они вместо вот этого вот в этом домкрате, вместо масла используют воду. И сейчас, когда сравнили вот эти на высотных зданиях испытания по корейской технологии, по американской, то получилось, что корейская оказалась лучше. И его OCEL, вот этот корейский тест, применяют сейчас больше. И он говорит, зачем вам надо платить американцам за этот Остерберг, когда можно сделать как типа русский Калашников, да, Russian Калашников.
Ну, понятно. Дело в том, что мы тоже применяем воду, и вернее те компании, которые используют, применяют воду, потому что те сваи, которые проводились испытания, они рабочие, они потом используются в качестве рабочих свай в свайном фундаменте. После того, как мы провели испытания, вода заменяется на бетон.
Professor, so you know, is more we use more American method because it is maybe we have some representative American company, maybe not so expensive because it is Russia rich country, the oil, gas, you know. money like, you know, like AEDA. No real money, да. Yes, I know, да. Он там в Корее действительно много компаний, вот, испытаний, поэтому как бы он уже опять проталкивает его, своего друга корейского, да. Все как учили, да. Везде как учили все нас. Везде надо проталкивать, пока есть возможность своих друзей и знакомых, да. Good lobby.
Олег Александрович, я все-таки быстро вопрос задам, хоть мы засиделись. Все-таки испытания проводились, это бареты или сваи бурнобивные? Вот в частности, интересный момент – это увеличение сопротивления по боковой поверхности, потому что вот…
Значит, то, что у нас проводились испытания и барет, и свай. Бареты проводились испытания на ОХТА-центре, потому что там вначале был проект по баретам. И там как раз проводились одновременно испытания 3 барет. А сваи проводились на ЛАХТА-центре. Значит, ну вот там у меня график был, там, по-моему, 2,5 метра было расстояние между баретами.
Это в свету или в осях?
Вот здесь показано. Так, значит, да, 2,5 метра в свету. Ну, 2,40.
Ну, просто вот интересно, за счет чего у соседней бареты может расти боковое сопротивление. Достаточно большое расстояние. Уплотнения грунта, по сути, при устройстве бареты нет.
Да.
То есть только за счет шероховатости поверхности несущая способность по боковой поверхности идет. То есть вот за счет чего роста?
Значит,
потому что сейчас, ну, все мы знаем, да, 50-60-й год достаточно большое количество было исследований по кустовому эффекту, и как бы большинство исследователей приходит к выводу, что в составе групп свайных фундаментов несущая способность падает, наоборот, не увеличивается. А тут получается диаметрально противоположный вывод. Поэтому вот интересно все-таки, за счет чего это происходит при таком расстоянии, в общем-то, ну и…
Ну, за счет… У нас же, вот видите, тут есть на графике есть испытания и одиночных свай, и свай в кусте. Вот одиночные сваи, вот 2 сваи было B4, B5, это одиночные сваи, они были испытаны практически такое же сопротивление, как и вот свай, который крайний B1, B3. А вот центральная свая получила большее значение сопротивления по боковой поверхности. Это, ну, на мой взгляд, происходит за счет того, что все-таки сваи достаточно длинные. И, значит, они располагались на глубине, вот испытания проводили на глубине 65 метров. Вот, значит, и достаточно большая часть свай нагружалась. То есть вот за счет того, что у нас и большие нагрузки были. То есть грунт, воспринимая, окружающий массив грунта, воспринимая нагрузку вертикальную от сваи, он, конечно, вступает в работу. Возникают у них, в грунте передаются за счет трения, грунт передается вертикальные напряжения. И за счет вертикальных напряжений большее обжатие происходит, соответствующим образом через коэффициент бокового давления увеличивается нагрузка боковая и на свай. Ну, здесь вот этот эффект проявляется не только для вот такого испытания, но и в процессе того, как мы нагружаем одиночную сваю. У нас тоже происходит увеличение сопротивления по боковой поверхности. Специально увеличение горизонтальных напряжений. Специально были проведены исследования с бурнобивными сваями. Причем изготовили эти бурнобивные сваи насухо. Установили датчики боковые. Потом забетонировали. И после того, как забетонировали, получили, что практически горизонтальные напряжения отсутствуют. Но в процессе того, как нагружалась свая, возникали вертикальные и горизонтальные напряжения, и вот за счет этого как раз у нас и происходит образование вот этого повышения несущей способности в процессе нагружения. Спасибо. Пожалуйста.
Спасибо, Олег Александрович, за прекрасный доклад. Очень интересные вопросы. Сейчас мы переходим к следующему докладу. Следующий доклад у нас будет читать Рафаэль Фаритович Шарафудинов, почему мне нравится, вот честно говоря, вот эта конференция, форум с участием изыскателей, потому что везде презентация дается отчество. Видите, очень легко предложить говорить о докладчике. Рафаэль Фаритович Шарафудинов является ведущим научным сотрудником по геотехнике и НИОСПа имени Герсиванова. И сегодня он читает доклад Consideration of pile work on the site surface in the rocky soils. So please, Dr. Шарафудинов.
Thank you, Professor Askar. And good day, ladies and gentlemen. I want to apologize, but my presentation will be in Russian. This presentation is devoted to skin friction of piles in rocks. In this presentation, I want to introduce the Russian experience. Если мы говорим о работе в скальных грунтах, то на сегодняшний день бытует мнение, ну, как бы оно исторически сложилось, что все сваи, которые находятся в скальных грунтах, это сваи стойкие. Хотя на самом деле опыт испытаний свай, опыт работы свай, анализ испытаний свай, да, показывает, что сваи стойкие, данный термин относится только к забивным сваям или сваям предварительно изготовленным, которые упираются в скалу. Если мы говорим о буронабивных сваях, то это сваи, взаимодействующие с грунтом, со скальным грунтом, причем по боковой поверхности преимущественно. Об этом мы остановимся. Ну, на сегодняшний день, если мы говорим о российских нормах, то нормы предусматривают два подхода по расчету свай, по несущей способности. Это то, что вы видите на слайде сверху, да, это известная формула, да, которая из СНИПа 202.01.85, наверное, да, которая по свайным фундаментам, она перекочевала у нас в СП-24 с некоторыми изменениями. И с недавнего времени вышли изменения номер 1, которые позволяют рассчитывать сваи по боковой поверхности. Данная формула, она коллегам зарубежным должна быть известна. Это Каллоуэй и Пун, получена как нижняя оценка несущей способности по результатам многочисленных испытаний. На этой формуле я задержусь чуть позже. Давайте пока перейдем к опыту. Если мы говорим об испытаниях свай для определения сопротивления по боковой поверхности, то, как вот Олег Александрович ранее рассказал, есть метод погружного домкрата и есть традиционный метод. Конечно, если мы говорим о скальных грунтах и о больших диаметрах, то следует отдавать предпочтение методу погружного домкрата, потому что это просто по экономическим соображениям лучше. Да, то есть нам не надо делать анкерные сваи. Мы можем развить большую нагрузку на сваях, мы можем сорвать сваи и получить реальную предельную несущую способность. Но есть некоторые аспекты при испытаниях. В частности, вот, например, есть требования к опытным сваям. То есть для того, чтобы мы достоверно оценили сопротивление по боковой поверхности свай, да и в ППТ тоже, необходимо сваи оборудовать датчиками, тензосистемой. Также необходимо удостовериться, что сваи имеют высокое качество, да, то есть подтверждать контролем сплошности. И также определять фактические деформационные характеристики бетона, потому что если мы говорим о плотных скалах, плотных скальных грунтах с малым количеством трещин, то их жесткость и прочность сопоставима с бетоном. Ну вот некоторые примеры несущей способности свай в скальных грунтах при строительстве зданий в Москве и Екатеринбурге. Ну вот тот опыт, о котором говорил Олег Александрович, это Сити 17-18, это недавно были проведены испытания. По-моему, 3 сваи, да, у нас было испытано. диаметром 1,5 метра, длиной 22 метра. Сопротивление по боковой поверхности составило от 80 до 280 тонн сил на квадратный метр. О чем это говорит? На самом деле несущая способность, она напрямую коррелирует от деформации, от перемещения, которую мы смогли дать сваи во время испытания. И здесь мы, конечно, вынуждены быть ограничены вот этой нагрузкой. Да? То есть нам всегда надо стараться, если мы хотим получить экономичное решение, дойти до предельной несущей способности. Испытания здесь выполнялись ячейкой ОЦЛ, привлекали компанию Load Test. На площадке Сити 16 участка, вот есть здесь патент Колыбин, Ладыжинский, Петрухин, Шулятьев, да, то есть была выполнена специальная опытная свая с раздельным испытанием по боковой поверхности и по пяте. Общая схема на слайде представлена, да. Испытания мы довели тогда до 3-3,2 тысяч тонн. Ну, для скальных грунтов это небольшие значения. Получили сопротивление по боковой поверхности порядка 33-36 тонн. И что интересно, сопротивление по пяте. Вот обратите внимание, это вот верхняя диаграмма. Да, то есть, в принципе, мы получили какое-то значимое сопротивление при перемещении более 40 миллиметров. Мы видим, здесь у нас график начинает выполаживаться, то есть там действительно пята начинает включаться в работу. Что 40 миллиметров – это много для сваи, то есть у нас в нормах на сегодняшний день предел несущей способности 40 миллиметров. Что касается вот Сити 12-13 участок, тоже были выполнены испытания фрагментов сваи. Были получены сопротивления по боковой поверхности от 150 до 250 тонн на квадратный метр. Вот одни из последних испытаний, которые мы выполняли. Дело в том, что в последние годы строительство высотных зданий перешло в фазу строительства верхних конструкций, и геотехники становится все меньше, новых данных все меньше, но тем не менее они появляются. Вот на западном округе Москвы сейчас строится высотное здание. Там выполнили испытания 6 свай сверху вниз. Получили тоже в условиях известняков Москвы 96-175 тонн сил. На самом деле, если мы говорим о территории России, то второй город в России по количеству высотных зданий – это Екатеринбург. Там очень близко находятся скальные грунты, там вообще идеальная площадка для подобных экспериментов. И вот кто не был в Екатеринбурге, рекомендую съездить, потому что вот за последние несколько лет город преобразился, стало очень много действительно красивых высотных зданий, причем нет такого вжимания территории, как в Москве, то есть когда мы с территории пытаемся, с земли, с каждого клочка земли пытаемся выжать по максимуму. То есть эти здания действительно красивые, они расположены на таком значительном расстоянии друг от друга, очень классный архитектурный ландшафт. Но вот в рамках одного из проектов мы выполняли испытания 6 свай, там были разные сопротивления по прочности нажатия грунтов, да, скальных грунтов. Ну вот получено вот такие вот результаты. То есть здесь мы смогли сорвать сваи. То есть испытание до 750 тонн, достаточно слабые скальные грунты, был срыв. По одной из свай мы видим, что как включилась работа пята. То есть и это было видно по датчикам информации. И теперь о международном опыте. Дело в том, что мы не можем находиться в отрыве от всего остального мира, да, и хотя у нас есть некоторые свои критерии по оценке несущей способности, ну, все-таки на мировой опыт надо опираться. И более того, на сегодняшний день в нормах внесена формула, которая получена на международном опыте. И вот давайте посмотрим, как они коррелируются с отечественным, с российским. Были проанализированы достаточно большое количество публикаций. Всего по публикациям удалось собрать 262 испытания сваи. Это были разные скальные породы, разные диаметры. Здесь рассматривались в том числе и микросваи, то есть анкера. Ну, в принципе, какая нам разница для сваи, да, там, при испытании. И вот что получено. Вот смотрите, здесь на слайде это общая выборка по всему миру, да, то есть то, что удалось собрать, вот эти 260 точек. На оси абсцисс это сопротивление сжатию образцов, на оси ординат это сопротивление боковой поверхности. И вот мы наложим сюда отечественный опыт. В принципе, мы никуда не ушли от мировых стандартов. Получены очень близкие данные. И это подтверждает то, что заложены нормативные документы, подходы, они, в общем-то, обеспечены, да, какой-то гарантией. Теперь два слова о сопротивлении сваи по нижнему концу. Это моя любимая часть презентации. Вот то, что было получено на некоторых участках Москва-Сити 16, я уже рассказывал. Москва-Сити 17 – это то, о чем говорил Олег Александрович, когда у нас сопротивление под нижним концом сваи начинает включаться при перемещении около 10 и более миллиметров. Если мы говорим о сопротивлении по боковой поверхности, то в этот момент примерно уже возникают какие-то предсрывные деформации. И вот что происходит на самом деле в забое скважины. То есть почему питание несет? Так потому что забой мы не можем зачистить. Вот сегодня коллеги из Боливии докладывали, прекрасный доклад, на мой взгляд, очень интересно, когда они предлагали разные методы по повышению несущей способности. Они действительно эффективны, они не настолько дорогие, особенно в сравнении с конечным результатом. Да? В итоге-то мы имеем экономию 40%, если их применяем. Так? Но вот на самом деле в забое скважины остается такой шлам, который сжимается и который подтверждает, что отсутствует у нас несущая способность по пите без специальных мероприятий. Ну вот еще одна фотография. Это вот коллеги, Станислав Олегович, Шулятьев, они спускались в скважину на Москва-Сити 17 в процессе выполнения работы и измеряли фактически забой. Ну, еще два слова. Сегодня коллеги также из Тайваня докладывали о том, что с использованием бэк-анализа они получали уточненные характеристики грунтов. Да? То есть, в принципе, если мы говорим о скальных грунтах, это достаточно актуальная вещь, потому что на сегодняшний день мы, как гражданские инженеры, мы плохо изучаем скальные грунты. Почему? Потому что скальные грунты имеют сетку трещин, да, у них разное раскрытие, разная шероховатость, разный заполнитель. И интерпретировать эти данные на реальные объекты с учетом масштаба сооружения достаточно сложно. Также влияет масштабный эффект. Часто мы получаем данные по модулям деформации, например, на основе образца, который мы смогли отобрать при бурении, а бурение у нас, как правило, одноколонковое, то есть это тот образец, который выжил и дошел до лаборатории. Естественно, мы у выжившего образца получаем бешеное сопротивление и бешеные модули. Но на самом деле, с учетом сетки трещин, неоднородности анизотропии, реальные деформационные характеристики будут отличаться, и это влияет на расчеты осадок. И одно дело мы считаем, когда осадки таких рядовых зданий, когда мы можем пренебречь осадкой свайного фундамента, ну, или вообще скальных грунтов. Но если мы говорим об осадках высотных зданий, большенагрузных зданий, плотин, то нам необходимо, конечно, учитывать масштабный эффект и реальные деформационные характеристики. Один из способов определения, ну, тот, который мы используем, продвигаем, и сейчас, по моим данным, даже в нормативные документы вошел, это обратные расчеты, это бэк-анализы по испытаниям свай. Но вот поэтому это тоже причина, почему необходимо устанавливать датчики. То есть с использованием и установкой датчиков мы всегда можем определить реальное распределение сопротивления по боковой поверхности, сколько в каком слое воспринимает и какие реальные деформационные характеристики у грунтов. Ну вот, например, на данном примере, да, вот здесь коллеги-геологи дали определенные значения модуля деформации, это вот левая колонка, да, для разных характеристик. А вот после бэк-анализа, после оптимизации мы получили более полные значения, которые характеризуют работу массива. Они другие, причем другие не только характеристики деформационные, но и прочностные. Это другая свая, в принципе, здесь такая же схожая ситуация. Если говорить по испытаниям в Екатеринбурге, которые мы выполняли, то там, вот здесь интересно, да, деформационные характеристики нам не дали. В первом приближении мы использовали эмпирические зависимости Хойка и Дидриха, да, 2006 года. И уже на втором этапе после оптимизации мы уточняли эти характеристики. Ну, там отличие где-то в 2-3 раза получилось по деформационным характеристикам. Еще что интересно, вот обратите внимание, здесь прочностные характеристики, которые получили геологи по испытаниям одиночных образцов. Да, ну, сцепление 940, 2800, 7000. килопаскалей. Ну, это много. По факту они были намного меньше по результатам испытаний. Ну и в целом такой подход, как мы видим, он у нас не новый, да, то есть его применяют в мире. Вот хороший пример, который я всегда привожу, это доклад профессора Каценбаха в 2017 году на форуме 100+, когда они для GD Tower, башни высотой 1 километр и 7 метров, использовали точно такие же подходы, как используем мы. Они обратными расчетами получали деформационные характеристики, которые позволили обеспечить надежность, подтвердить надежность объектов. У меня все. Спасибо за внимание.
Спасибо большое, Рафаэль Фаритович. Пожалуйста, вопросы. Очень интересный доклад. Так, some questions from our auditorium. No questions. So, большое спасибо за ваше участие, особенно большое спасибо за участие, особенно вот молодежь. Вот я так понял, что это 6-й курс, специалитет, все горящие глаза. Я думаю, что впереди нас ждет армия геотехников с МГСУ и с НОПРИЗа, изыскателей. Так что мы спокойно можем жить дальше, да. Мы знаем, что за нами можно кому передать эстафету. Большое спасибо за докладчиков, особенно за модераторов, которые, видите, с начала до конца выдержали этот марафон. И очень большая секция, наша секция самая последняя. Вот у нас сидит организатор конференции Александр Валерьевич Сельцов, который, значит, смотрит, и второй год он убеждается, что мы самые активные, да. Самые поздно уходим, самые ранее приходим, да. Большое спасибо. Жду вас в Санкт-Петербурге на следующей неделе, 27-29 октября. Марафон продолжается, потому что до пандемии мы должны поработать. До локаута, до нашего закрытия нашего хода на 7 дней мы должны четко поработать. Спасибо.